Why weren't we pushing towards economic fusion and new materials and new methods of heat extraction and so forth? Because everybody knew fusion was 40 years away. And now it's 4 years away.
The following is a conversation with Dennis Whyte, nuclear physicist at MIT and the director of the MIT Plasma Science and Fusion Center. This is the Lex Fridman podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Dennis Whyte. Let's start with a big question. What is nuclear fusion?
It's the underlying process that powers the universe. So as the name implies, it fuses together or brings together two different elements, technically nuclei, that come together. And if you can push them together close enough that you can trigger essentially a reaction, what happens is that the element typically changes. So this means that you change from one element to another, chemical element to another. Underlying what this means is that you change the nuclear structure. This rearrangement through E equals mc squared releases large amounts of energy. So fusion is the fusing together of lighter elements into heavier elements. And when you go through it, you say, oh, look, so here were the initial elements, typically hydrogen, and they had a particular mass, rest mass, which means just the mass when they're with no kinetic energy. And when you look at the product afterwards, it has less rest mass. And so you go, well, how is that possible? Because you have to keep mass, but mass and energy are the same thing, which is what E equals mc squared means. And the conversion of this comes into kinetic energy, namely energy that you can use in some way. And that's what happens in the center of stars. So fusion is literally the reason life is viable in the universe.
So fusion is happening in our sun. And what are the elements?
The elements are hydrogen that are coming together. It goes through a process which is probably gets a little bit too detailed, but it's a somewhat complex catalyzed process that happens in the center of stars. But in the end, stars are big balls of hydrogen, which is the lightest, it's the simplest element, the lightest element, the most abundant element. Most of the universe is hydrogen. And it's essentially a sequence through which these processes occur that you end up with helium. So those are the primary things. And the reason for this is because helium has features as a nucleus, like the interior part of the atom, that is extremely stable. And the reason for this is helium has 2 protons and 2 neutrons. These are the things that make up nuclei, that make up all of us, along with electrons. And because it has 2 pairs, it's extremely stable. And for this reason, when you convert the hydrogen into helium, it just wants to stay helium, and it wants to release kinetic energy. So stars are basically conversion engines of hydrogen into helium. And this also tells you why you love fusion. I mean, because our sun will last 10 billion years approximately. That's how long the fuel will last.
But to do that kind of conversion, you have to have extremely high temperatures.
It is one of the criteria for doing this, but it's the easiest one to understand. And why is this? It's because effectively what this requires is that these hydrogen ions, which is really the bare nucleus, so they have a positive charge. Everything has a positive charge of those ones. Is that to get them to trigger this reaction, they must approach within distances which are like the size of the nucleus itself, because the nature, in fact, what it's really using is something called the strong nuclear force. There's 4 fundamental forces in the universe. This is the strongest one, but it has a strange property, is that while it's the strongest force by far, it only has impact over distances which are the size of a nucleus. So to put that into, what does that mean? It's a millionth of a billionth of a meter. Okay. Incredibly small distances. But because the distances are small and the particles have charge, they want to push strongly apart. Namely, they have repulsion that wants to push them apart. So it turns, when you go through the math of this, the average velocity or energy of the particles must be very high to have any significant probability of the reactions happening. And so the center of our sun is at about 20 million degrees Celsius. And on Earth, this means it's one of the first things we teach, entering graduate students. You can do a quick You can do a quick, basically power balance, and you can determine that on Earth it requires a minimum temperature of about 50 million degrees Celsius on Earth
To perform fusion.
to get enough fusion that you would be able to get energy gain out of it. So you can trigger fusion reactions at lower energy, but they become almost vanishingly small at lower temperatures than that.
First of all, let me just linger on some crazy ideas. So, one, the strong force, just stepping out and looking at all of physics. Is it weird to you that there's these forces and they're very particular, like it operates at a very small distance, and then gravity operates at a very large distance, and they're all very specific, and the standard model describes three of those forces extremely well, and this
is one of them. And
this is one of them, and it's just all kind of works out. There's a big part of you that's, an engineer. Did you step back and almost look at the philosophy of physics?
So it's interesting because as a scientist, I see the universe through that lens of essentially the interesting things that we do are through the forces that get used around those, and everything works because of that. Richard Feynman had, I don't know if you ever read Richard Feynman. It's a little bit of a tangent, but
he's never been on the podcast.
He's never been on the podcast. He was unfortunately passed away, but one of like a hero to almost all physicists. And then part of it was because of what you said. He kind of looked through a different lens at these, what typically look like very dry, like equations and relationships. And he kind of, I think he brought out the wonder of it in some sense, right? For those. He posited what would be, if you could write down a single, not even really a sentence, but a single concept that was the most important thing scientifically that we knew about. That, in other words, you had only one thing that you could transmit, like a future or past generation. It was very interesting. It was so it's not what you think. It wasn't like, strong nuclear force or fusion or something like this. And it's very profound, which was that the reason that matter operates the way that it does is because all matter is made up of individual particles that interact each other through forces. That was it.
So just
that atomic theory, basically.
Yeah.
Which is like, wow, that's like so simple, but it's not so simple. It's because like, who thinks about atoms that they're made out of? Like, this is a good question I give to my students. How many atoms are in your body? Like, almost no students can answer this, but to me, that's like a fundamental thing. Yeah. By the way, it's about 10 to the 28.
10 to the 28.
So that's trillion, million, trillion, or something like that. Yes. Yeah.
So one thing is to think about the number, and the other is to start to really ponder the fact
that it all holds together.
Yeah, it all holds together, and you're actually that. You're more that than you are anything else.
Yes, exactly. Yeah. No, I mean, there are people who do study such things, of the fact that if you look at for example, the ratios between those fundamental forces, people have figured out, if this ratio was different by some factor, like a factor of 2 or something, I was like, this would all like not work. Mm-hmm. And you look at the sun, right? It's like, so it turns out that there are key reactions that if they had slightly lower probability, no star would ever ignite. Mm-hmm. And then life wouldn't be possible.
It does seem like the universe set things up for us that it's possible to do some cool things, but it's challenging. So that keeps it fun for us.
Yeah, that's the way I look at it. I mean, the multiverse model is an interesting one because there are quantum scientists who look at and figure. It's like, yeah. Like quantum science perhaps tells us that there are almost an infinite, variety of other universes. But the way that it works probably is it's almost like a form of natural selection. It's like, well, the universes that didn't have the correct or interesting relationships between these forces, nothing happens in them. So almost by definition, the fact that we're having this conversation means that we're in one of the interesting ones by default.
Yeah, one of the somewhat interesting, but there's probably super interesting ones where I tend to think of humans as incredible creatures. Our brain is an incredible computing device, but I think we're also extremely cognitively limited. I can imagine alien civilizations that are much, 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 much more intelligent in ways we can't even comprehend in terms of their ability to construct models of the world, to do physics and mathematics.
I would see it in a slightly different way. It's because we have creatures that live with us on the earth that have cognition, right? That understand and move through their environment. but they actually see things in a way, or they sense things in a way which is so fundamentally different. It's really hard. Like it's the problem is the translation, not necessarily intelligence. So it's the perception of the world. So I have a dog, and when I go out and I see my dog like smelling things, there's a realization that I have that he sees or senses the world in a way that I can never, like, I can't understand it because I can't translate my way to this. We get little glimpses of this as humans, though, by the way, because there are some parts of it, for example, optical information, which comes from light, is that now, because we've developed the technology, we can actually see things. I get this, as one of my areas of research is spectroscopy. So this means the study of light, and I get to quote unquote see things or representations of them from, the far infrared all the way to like hard X-rays, which is several orders of magnitude of the light intensity. But our own human eyes like see a teeny little sliver of this.
Yeah.
So that even like bees, for example, see a different place than we do. So I don't. I think if you think of, there's already other intelligences like around us in a way, in a limited way, because of the way they can communicate. But it's like those are already baffling in many ways. Yeah.
So if we just focus in on the senses, there's already a lot of diversity, but there's probably things we're not even considering as possibilities.
Yes.
For example, whatever the heck consciousness is, could actually be a door into understanding some physical phenomena haven't even begun understanding. So just like you said, spectroscopy, there could be a similar kind of spectrum for consciousness that we're like these dumb the descendants of apes, like walking around. It sure feels like something to experience the color red, but like we don't have. It's the same as in the ancient times. You experience physics, you experience light. Yeah. It's like, oh, it's bright, and
yeah.
And you construct kind of semi.
Well, it's interesting. We might actually experience this faster than we thought, because we might be building another kind of intelligence.
Yeah, and that intelligence will explain to us how silly we are.
There was an email thread going around the professors in my department already of so what is it going to look like to figure out if students have actually written their term papers, or it's chat GPT. It was so, as usual, we tend to be empiricists in my field. So of course they were in there like trying to figure out if it could answer like questions for a qualifying exam to get into the PhD program at MIT, which was they didn't do that well at that point. But of course, this is just the beginning of it. So we have some interesting ones to go.
Eventually, both the students and the professors will be replaced by ChatGPT.
Yeah,
and we'll sit on the beach.
I really recommend, this. I don't know if you've ever seen them. It's called "The Day the Universe Changed." This is
that a movie?
James Burke.
Yeah.
He's a science historian based in the UK. He had a fairly famous series on public television called Connections, I think it was. But the one that I really enjoyed was "The Day the Universe Changed," and the reason for the title of it was that. He says the universe is what we know and perceive of it. So when there's a fundamental insight as to something new, the universe for us changes. Of course, the universe from an objective point of view is the same as it was before, but for us, it has changed. So he walks through these moments of perception in the history of humanity that like changed what we were, right? And so as I was thinking about coming to discuss this, people see fusion. Oh, it's still far away, or it's been slow progress. It's like when my godmother was born, like people had no idea how stars worked. So you talk about like that day, that insight, the universe changed. It's like, oh, this is and they still didn't understand all the parts of it, but they basically got it. It's like, oh, because of the understanding of these processes, it's like we unveiled the reason that there can be life in the universe. That's probably one of those days the universe changed, right?
Mm-hmm.
Yeah.
And
that was in the 1930s. Yeah.
It seems like technology is developing faster and faster and faster. Yeah. I tend to think, just like with ChatGPT, I think this year might be extremely interesting, just with how rapid and how profitable the efforts in artificial intelligence are, that just stuff will happen where our whole world is transformed like this, and there's a shock, and then next day you kind of go on and you adjust immediately. You probably won't have a similar kind of thing with nuclear fusion with energy because there's probably going to be an opening ceremony and stuff.
Yes.
An announcement. It'll take months. But
Yeah.
with digital technology, you can just have a immediate transformation of society, and then it'll be this gasp, and then you kind of adjust like
Yeah.
we always do, and then you don't even remember, just like with the internet and so on,
Yeah.
how the days were before.
And how it worked before, right? Yeah. I mean, fusion will be because it's energy. Its nature is that it will be, and anything that has to do with energy use tends to be a slower transition. But they're the most, I would argue, some of the most profound
Yes.
transitions that we make. I mean, the reason that we can live like this and sit in this
Mhm.
building and have this podcast and people around the world is at its heart is energy use,
Mhm.
and it's intense energy use that came from the evolution of starting to use intense energies at the beginning of the Industrial Revolution up to now. It's a bedrock actually of all of these, but it doesn't tend to come overnight.
Yeah.
Yeah.
And some of the most important, some of the most amazing technology is one we don't notice because we take it for granted because it enables this whole thing.
Yeah, exactly. Which
And
is energy, which is amazing for how fundamental it is to our society and way of life is a very poorly understood concept, actually. Just even energy itself, people confuse energy sources with energy storage, with energy transmission. These are different physical phenomena, which are very important. So, for example, you buy an electric car and you go, oh, good, I have an emission free car. And but it's like, so what, why do you say that? Well, it's because if I draw the circle around the car, I have electricity and it doesn't emit anything. Okay, but you plug that into a grid where you follow that wire back, there could be a coal power plant
Mhm.
or a gas power plant at the end of that. Oh, really? You mean so this isn't like carbon free? Oh, and it's not their fault. It's just, they don't, like, the car isn't a source of energy. The underlying source of energy was the combustion of the fuel back somewhere. Yeah.
Plus, there's also a story of how the raw materials are mined
Yeah.
in which parts of the world, with sort of basic respect or deep disrespect of human rights that happens in that mining. So the whole supply chain, there's a story there that's deeper than just a particular
Yes.
electric car with a circle
Yeah.
around it.
And the physics or the science of it too is the energy use that it takes to do that digging up, which is
Yeah.
also important and all that. Yeah. Anyway, so we,
Yeah.
we wandered away from fusion, but yes,
No, it's a beautiful
but
stroll.
it's very important actually to in the context of this, just because those of us who work in fusion and these other kinds of sort of disruptive energy technologies, it's interesting. I do think about, like, what is it going to mean to society to have an energy source that is like this, that would be like fusion, which has such completely different characteristics. For example, free unlimited access to the fuel, but it has technology implications. So what does this mean geopolitically? What does it mean for how we distribute wealth within our society? It's very difficult to know, but
Yeah.
probably profound. Yeah.
We're gonna have to find another reason to start wars. Um,
Uh,
instead of resources, we're gonna have to figure something
we've done a
else out.
pretty good job of that over
Yeah, we're
the
very
course of our
clever.
histories. Yeah.
So we talked about the forces of physics, and again, sticking to the philosophical before we get to the specific technical stuff. E equals mc squared. You mentioned. How amazing is that to you? That energy and mass are the same.
Yeah.
And what does that have to do with nuclear fusion?
So it has to do with everything we do. It's the fact that energy and mass are equivalent to each other. They're just the way we usually comment to it is that they're just energy, just in different forms.
Can you intuitively understand that?
Yes, but it takes a long time. I haven't for a while, but usually, often I teach the introductory class for incoming nuclear engineers, and so we put this up as an equation, and we go through many iterations of using this, to how you derive it, how you use it, and so forth. And then usually in the final exam, I would basically take all the equations that I've used before and I flip it around. I basically, instead of thinking about energy is equal to mass, it's sort of mass is equal to energy. And I ask the question in a different way. And usually about half the students don't get it. It takes a while it's to get that intuition. Yeah. So in the end, it's interesting is that this is actually the source of all free energy, because that energy that we're talking about is kinetic energy if it can be transformed from mass. So it turns out even even though we used equals mc squared. This is burning coal and burning gas and burning wood is actually still equals mc squared. The problem is that you would never know this because the relative change in the mass is incredibly small. By the way, which comes back to fusion, which is that E equals mc squared. Okay, so what does this mean? It tells you that the amount of energy that is liberated in a particular reaction when you change mass has to because c squared that's the speed of light squared.
It's a large number.
It's a very large number, and it's totally constant everywhere in the universe, which is
another weird thing.
Which is another weird thing, and in all rest frames, and actually the relativity stuff gets more difficult conceptually until you get through it. Anyway, so you go to that and what that tells you is that it's the relative change in the mass will tell you about the relative amount of energy that's liberated. And this is what makes fusion, and you asked about fission as well too. This is what makes them extraordinary. It's because the relative change in the mass is very large as compared to what you get like in a chemical reaction. In fact, it's about 10 million times larger. And that is at the heart of why you use something like fusion. It's because that is a fundamental of nature. Like you can't beat that. So of whatever you do, if you're thinking about, and why do I care about this? Well, because mass is like the fuel, right? So this means gathering the resources that it takes to gather a fuel, to hold it together, to deal with it, the environmental impact it would have. And fusion will always have 20 million times the amount of energy release per reaction that you get of those. So this is why, we consider it the ultimate like environmentally friendly energy source is because of that.
So is it correct to think of mass broadly as a kind of storage of energy?
Yes.
You mentioned it's environmentally friendly. So nuclear fusion is a source of energy. It's cheap, clean, safe. So easy access to fuel and virtually unlimited supply, no production of greenhouse gases, little radioactive waste produced allegedly.
Mm-hmm.
Can you sort of elaborate why it's cheap, clean, and safe?
I'll start with the easiest one, cheap. It is not cheap yet because it hasn't been made at a commercial scale.
Time flies when you're having fun. But yes.
Yeah.
But yes, not yet.
But
we'll talk about
actually, we'll come back to that because this is cheap or a more technically correct term that it's economically interesting is really the primary challenge actually of fusion at this point. But I think we can get back to that. So what were the other ones you said?
So cheap. Actually, when we're talking about cheap, we're thinking like asymptotically. Like if you take it forward several hundred years, that's sort of because of how much availability there is of resources to use
of the fuel.
Yeah, of the fuel.
We should separate those two. The fuel is already cheap. It's basically free, right? Yeah. What do you mean by basically free? So if we were to be using fusion fuel sources to power and it's like that's all we had was fusion power plants around, and we were doing it. The fuel cost per person or something like 10 cents a year. It's like it's free. Okay. This is why it's hard to, in some ways, I think it's hard to understand fusion because people see this and go, oh, if the fuel is free, this means the energy source is free because we're used to energy sources like this. So we spend resources and drill to get gas or oil, or we chop wood, or we make coal, we find coal or these things. All right. So fusion, this is what makes fusion. And it's also, it's not an intermittent renewable energy source like wind and solar. So it's like, but this makes it hard to understand. So if you're saying the fuel is free, why isn't the energy source free? And it's because of the necessary technologies which must be applied to basically recreate the conditions which are in stars. Mm-hmm. In the center of stars, in fact. So there's only one natural place in the universe that fusion energy occurs. That's in the center of stars. So that's going to bring a price to it, depending on the cost and the size and complexity of the technology that's needed to recreate those things.
And we'll talk about the details of those technologies and which parts might be expensive today and which parts might be expensive in 200 years.
Exactly. It will have a revolution in it. I'm certain of it. So about clean. So clean is at its heart. What it does is it basically converts hydrogen into it's heavier forms of hydrogen. The most predominant one that we use on Earth and converts it into helium and some other products, but primarily helium is the product that's left behind. So helium, safe, inert gas, you know. In fact, that's actually what our sun is doing. It's eventually going to extinguish itself because it'll just make so much helium that it doesn't do that. So in that sense, clean because there's no emissions of carbon or pollutants that come directly from the combustion of the fuel itself.
And safe.
Safe, yeah.
We're talking about very high temperatures.
Yeah. So this is also the counterintuitive thing. So I told you temperatures, which like 50 million degrees, or it actually tends to be more like about 100 million degrees is really what we aim for. So how can 100 million degrees be safe? And it's safe because this is so much hotter than anything on Earth, where everything on Earth is at around 300 Kelvin. It's around a few tens of degrees Celsius. And what this means is that in order to get a medium to those temperatures, you have to completely isolate it from anything to do with terrestrial environment. It can have no contact, like with anything on Earth, basically. So this means this is the technology that I just described, is that it fundamentally what it does is it takes this fuel and it isolates it from any terrestrial conditions so that it has no idea it's on Earth. It's not touching any object that's at room temperature.
Including the walls of the containment.
Including the walls of the containment building or containment device, or even air or anything like this. So it's that part that makes it safe in this, and there's actually another aspect to it, but that fundamental part makes it so safe. In the mainline approach to fusion is also that it's very hot, but there's very, very few particles at any time in the thing that would be the power plant. Actually, the more correct way to do it is you say there's very few particles per unit volume. So in a cubic centimeter and a cubic meter or something like that. So we can do this. So right now although we don't think of air really as there's atoms floating around us and there's a density, because if I wave my hand, I can feel the air pushing against my face. That means we're in a fluid or a gas, which is around us. That has a particular number of atoms per cubic meter. Right. So this actually turns out to be 10 to the 25th. So this is one with 25 zeros behind it per cubic meter. So we can figure out a cubic meter is about like this, the volume of this table, like the whole volume of this table. Okay, very good. So like fusion, or it's a few of those. So fusion, like the mainstream one of fusion, like what we're working on at MIT, will have 100,000 times less particles per unit volume than that. So this is very interesting because it's extraordinarily hot, 100 million degrees, but it's very tenuous. And what matters from the engineering and safety point of view is the amount of energy which is stored per unit volume, because this tells you about the scenarios and that's what you worry about, because when those kinds of energies are released suddenly, it's like, what would be the consequences, right? So the consequences of this are essentially zero, because that's less energy content than boiling water.
Because of the low density?
Because of the low density. So if you take water is at about 100 million to 1 billion times more dense than this. So even though it's at much lower temperature, it's actually it has more energy content. So for this reason, one of the ways that I explain this is that if you imagine a power plant that's like powering Cambridge, Massachusetts, like if you were to, which you wouldn't do this directly, but if you went like this on it, it actually extinguishes the fusion because it gets too cold immediately. Yeah. So that's the other one. And the other part is that it does not, because it works by staying hot rather than a chain reaction, it can't run out of control. That's the other part of it. So by the way, this is what very much distinguishes it from fission. It's not a process that can run away from you because it's basically thermally stable.
What does thermally stable mean here?
That means is that you want to run it at the optimization in temperature such that if it deviates away from that temperature, the reactivity gets lower. And the reason for this is because it's hard to keep the reactivity going. Like it's a very hard fire to keep going, basically.
Also, it doesn't run away from you.
It can't run away.
So how difficult is the control there to keep it at that?
It varies from from concept to concept, but in generally it's fairly easy to do that. And the easiest thing, it can't physically run away from you, because the other part of it is that there's just, at any given time, there's a very, very small amount of fuel available to fuse anyway. So this means that that's always intrinsically limited to this. So even if the power consumption of the device goes up, it just kind of burns itself out immediately. Yeah.
So you are just to take another tangent on a tangent, you're the director of MIT's Plasma Science and Fusion Center.
That's right.
We'll talk about, maybe you can mention some interesting aspects of the history of the center, in the broader history of MIT, and maybe broader history of science and engineering in the history of human civilization, but also just to linger on the safety aspect.
Yeah.
How do you prevent, some of the amazing reactors that you're designing? How do you prevent from destroying all of human civilization in the process? What's the safety protocols?
Fusion is interesting because it's not really directly weaponizable, because what I mean by that is that you have to work very hard to make these conditions at which you can get energy gain from fusion. And this means that when we design these devices with respect to application in the energy field, is that while they will, because they're producing large amounts of power and they will have hot things inside of them, this means that they have a level of industrial hazard, which is very similar to like you would have like in a chemical processing plant or anything like that. And any kind of energy plant actually has these as well too. But the underneath it core technology like can't be directly used in a nefarious way because of the power that's being emitted. It just basically, if you try to do those things, typically it just stops working.
So the safety concerns have to do with just regular things that like equipment malfunctioning, melting of equipment, like all this kind of stuff that has nothing to do with fusion necessarily.
Yeah, I mean, usually what we worry about is the viability, because in the end we build pretty complex objects to realize these requirements, and so what we try really hard to do is like not damage those components. But those are things which are internal to the fusion device, and this is not something that you would consider about like it would, as you say, destroy human civilization, because that release of energy is just inherently limited because of the fusion process. So it doesn't say that there's zero. So you asked about the other feature of it, that it's safe. So it is. The process itself is intrinsically safe, but because it's a complex technology, you still have to take into consideration aspects of the safety. So it produces ionizing radiation instantaneously. So you have to take care of this, which means that you shield it. You think of like your dental x-rays or treatments for cancer and things like this. We always shield ourselves from this. So we get the beneficial effects, but we minimize the harmful effects of those. So there are those aspects of it as well too. Yeah.
So we'll return to MIT's Plasma Science and Fusion Center, but let us linger on the destruction of human civilization, which brings us to the topic of nuclear fission. What is that? So the process that is inside nuclear weapons and current nuclear power plants.
So it relies on the same underlying physical principle, but it's exactly the opposite of which actually the names imply. Fusion means bringing things together. Fission means splitting things apart. So fission requires the heaviest instead of the lightest, and the most unstable versus the most stable elements. So this tends to be uranium, or plutonium, primarily uranium. So take uranium. So uranium-235 is one of this is one of the heaviest unstable elements. And what happens is that this is fission is triggered by the fact that one of these subatomic particles, the neutron, which has no electric charge, basically gets in proximity enough to this and triggers an instability effectively inside of this what is teetering on the border of instability, and basically splits it apart. And that's the fission, right? The fissioning. And so when that happens, because the products that are, and kind of roughly splits in two, but it's not even that, it's actually more complicated. It splits into this whole array of lighter elements and nuclei. And when that happens, there's less rest mass laugh than the original one. So it's actually the same. So it's rearrangement of the strong nuclear force that's happening. But that's the source of the energy. And so in the end, it's like, so this is a famous graph that we show everybody is basically, it turns out every element that exists in the periodic table, all the things that make up everything, have a. Remember, you asked a good question. It was like, so should we think of mass as being the same as stored energy? Yes. So you can make a plot that basically shows the relative amount of stored energy in all of the elements that are stable and make up basically the world, okay, in the universe. And it turns out that this one has a maximum amount of stability or storage at iron. So it's kind of in the middle of the periodic table because this goes from, it's roughly that. And so what that means is that if you take something heavier than iron, like uranium, which is more than twice as heavy than that, and you split apart, if somehow just magically you can just split apart its constituents and you get something that's lighter, that will, because it moves to a more stable energy state, it releases kinetic energy. That's the energy that we use. Kinetic energy meaning the movement of things. So it's actually an energy you can do something with. And fusion, it sits on the other side of that because it's also moving towards iron, but it has to do it through fusion together. So this leads to some pretty profound differences. As I said, they have some underlying physics or science proximity to each other, but they're literally the opposite. So fusion, why is this? It actually goes into practical implications of it, which is that fission could happen at room temperature. It's because this neutron has no electric charge, and therefore it's literally room temperature neutrons that actually trigger the reaction. So this means in order to establish what's going on with it, and it works by a chain reaction, is that you can do this at room temperature. So Enrico Fermi did this like on a university campus, University of Chicago campus. The first sustained chain reaction was done underneath a squash court with a big blocks of graphite. It was still, don't get me wrong, an incredible human achievement, right? But that's, and then you think about fusion, I have to build a contraption of some kind that's going to get to 100 million degrees. Okay, wow, that's a big difference. The other one is about the chain reaction, that namely fission works by the fact that when that fission occurs, it actually produces free neutrons. Free neutrons, particularly if they get slowed down to room temperature, can trigger other fission reactions if there's other uranium nearby or fissile materials. So this means that the way that it releases energy is that you set this up in a very careful way such that on average, every reaction that happens exactly releases enough neutrons and slows down that they actually make another reaction, exactly one. And what this means is that because each reaction releases a fixed amount of energy, blah, 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 you do this, and then in time, this looks like just a constant power output. So that's how a fission power plant works.
And so there's control of the chain reactions is extremely difficult and extremely important for
It's very important.
fission.
And when you intentionally design it, that it creates more than one fission reaction per starting reaction, then it exponentiates away. Which is what a nuclear weapon is.
Yeah. So how does an atomic weapon work? How does a hydrogen bomb work? Asking for a friend.
Yeah. Yeah. So at its heart, what you do is you very quickly put together enough of these materials that can undergo fission with room temperature neutrons, and you put them together fast enough that what happens is that this process can essentially grow mathematically, like very fast. And so this releases large amounts of energy. So that's the underlying reason that it works. So you've heard of a fusion weapon. So this is interesting, is that but it's dislike fusion energy in the sense that what happens is that you're using fusion reactions but it increases the gain actually of the weapon rather than it's not a pure, at its heart, it's still a fission weapon. You're just using fusion reactions as a sort of an intermediate catalyst basically to get even more energy out of it. But it's not directly applicable to be used in an energy source.
Does it terrify you, just again, to step back at the philosophical, that humans have been able to use physics and engineering to create such powerful weapons?
I wouldn't say terrify. I mean, we should be This is the progress of humanity. Every time that we've gotten access, you talk again, the day the universe changed. Those really changed when we got access to new kinds of energy sources. But every time you get access, and typically what this meant was you get access to more intense energy, right? That's what that was. And so the ability to move from burning wood to using coal to using gasoline and petroleum, and then finally to use this is that both the potency and the consequences are elevated around those things.
It's just like you said, the way that nuclear fusion would change the world, I don't think, unless we think really deeply, we'll be able to anticipate some of the things we can create. There's going to be a lot of amazing stuff, but then that amazing stuff is going to enable more amazing stuff and more, unfortunately, or depending how you see on it, more powerful weapons.
Well, yeah, but see, that's the thing. Fusion breaks that trend in the following way. So fusion doesn't work on a chain reaction. There's no chain reaction, zero. So this means it cannot physically exponentiate away on you because it works. And actually, this is why stars, by the way, we know this already. It's why stars are so stable, why most stars and suns are so stable. It's because they are regulated through their own temperature and their heating. Because what's happening is not that there's some probability of this exponentiating away, is that the energy that's being released by fusion basically is keeping the fire hot. Mm-hmm. And these tend to be, and when it comes down to thermodynamics and things like this, there's a reason, for example, it's pretty easy to keep a constant temperature like in an oven and things like this. It's the same thing in fusion. So this is actually one of the features that I would argue fusion breaks the trend of this, is that it has more energy intensity than fission on paper, but it actually does not have the consequences of control and sort of rapid release of the energy, because it's actually the physical system just doesn't want to do that. Yeah,
we're gonna have to look elsewhere for the weapons with which we fight World War III. Fair enough. So, what is plasma? That you may have not mentioned. You mentioned ions and electrons and so on.
Plasma.
So what is plasma? What is the role of plasma in nuclear fusion?
So plasma is a phase of matter or state of matter. So unfortunately, our schools don't. It's like, I'm not sure why this is the case, but all children learn the three phases of matter, right? So, and what does this mean? So we'll take like water as an example. So if it's cold, it's ice. It's in a solid phase, right? And then if you heat it up, it's the temperature that typically sets the phase. Although it's not only temperature. So you heat it up and you go to a liquid, and obviously it changes its physical properties because you can pour it and so forth, right? And then if you heat this up enough, it turns into a gas, and a gas behaves differently because there's a very sudden change in the density. Actually, that's what's happening. So it changes by about a factor of 10,000 in density from the liquid phase into when you make it into steam at atmospheric pressure. All very good. Except the problem is they forgot like what happens if you just keep elevating the temperature.
You don't want to give kids ideas. They're going to start experimenting, and they're going to start heating up the gas.
It's good to start doing anyway. So it turns out that once you get above, it's approximately 5 or 10,000 degrees Celsius, then you hit a new phase of matter. And actually, that's the phase of matter that is for pretty much all the temperatures that are above that as well too. And so what does that mean? So it actually changes phase. So it's a different state of matter. And the reason that it becomes a different state of matter is that it's hot enough that what happens is that the atoms that make up, remember, go back to Feynman, right? Everything's made up of these individual things, these atoms. But atoms can actually themselves be, which are made of nuclei, which contain the positive particles and the neutrons, and then the electrons, which are very, very light, very much less mass than the nucleus, and that surround us. This is what makes up an atom. So a plasma is what happens when you start pulling away enough of those electrons that they're free from the ions. So almost all the atoms that make up us up and this water and all that, the electrons are in tightly bound states, and basically they're extremely stable. Once you're at about 5,000 or 10,000 degrees, you start pulling off the electrons. And what this means is that now the medium that is there, its constituent particles mostly have net charge on them. So why does that matter? It's because now this means that the particles can interact through their electric charge. In some sense, they were when it was in the atom as well, too. But now that they're free particles, this means that it fundamentally changes the behavior. It doesn't behave like a gas. It doesn't behave like a solid or a liquid. It behaves like a plasma, right? And so why is it disappointing that we don't speak about this? It's because 99% of the universe is in the plasma state. It's called stars. And in fact, our own sun, at the center of the sun is clearly a plasma. But actually the surface of the sun, which is around 5,500 Celsius, is also a plasma. Because it's hot enough that is that. In fact, the things that you see, sometimes you see these pictures from the surface of the sun, amazing, like satellite photographs of like those big arms of things and of light coming off of the surface of the sun and solar flares. Those are plasmas.
What are some interesting ways that this fourth state of matter is different than gas?
Let's go to how a gas works, right? So the reason a gas, and it goes back to Feynman's brilliance in saying that this is the most important concept. The reason actually solid, liquid, and gas phases work is because the nature of the interaction between the atoms changes. And so in a gas, you can think of this as being this room, and the things, although you can't see them, is that the molecules are flying around, but then with some frequency, they basically bounce into each other. Mm-hmm. And when they bounce into each other, they exchange momentum and energy around on this. And so it turns out that the probability and the distances and the scattering of those of what they do, it's those interactions that set the about how a gas behaves. Mm-hmm. So what do you mean by this? So for example, if I take an imaginary test particle of some kind, like I spray something into the air that's got a particular color. In fact, you can do it in liquids as well too. Like how it gradually will disperse away from you. This is fundamentally set because of the way that those particles are bouncing into each other.
The probabilities of those particles bouncing.
The rate that they go at and the distance that they go at and so forth. So this was figured out by Einstein and others at the beginning of the Brownian motion, all these kinds of things. These were set up at the beginning of the last century, and it was really like this great revelation. Wow, this is why matter behaves the way that it does. Like, wow. But it's really like, and also in liquids and in solids, like what really matters is how you're interacting with your nearest neighbor. Mm-hmm. So you think about that one, the gas particles are basically going around until they actually hit into each other, though, they don't really exchange information. And it's the same in a liquid, you're kind of beside each other, but you can kind of move around. And in a solid, you're literally like stuck beside your neighbor. You can't move. Plasmas are weird in the sense is that it's not like that. So, and it's because the particles have electric charge. This means that they can push against each other without actually being in close proximity to each other. That's not an infinitely true statement, which gets a little bit more technical. But basically, this means that you can start having action or exchange of information at a distance. And that's, in fact, the definition of a plasma, that it says these have a technical name. It's called a Coulomb collision. It just means that it's dictated by this force which is being pushed between the charged particles. Is that the definition of a plasma is a medium in which the collective behavior is dominated by these collisions at a distance. So you can imagine then this starts to give you some strange behaviors. Which I could quickly talk about. Like, for example, one of the most counterintuitive ones is as plasmas get more hot, as they get higher in temperature, then the collisions happen less frequently. It's like what? That doesn't make any sense. When particles go faster, you think they would collide more often. But because the particles are interacting through their electric field, when they're going faster, they actually spend less time in the influential field of each other, and so they talk to each other less in an energy and momentum exchange point of view. Just one of the counterintuitive aspects of plasmas,
which is probably very relevant for nuclear fusion.
Yes, exactly.
So if I can try to summarize what a nuclear fusion reactor is supposed to do. So you have a couple of elements. What are usually the elements?
Usually deuterium and tritium, which are the heavy forms of hydrogen.
You have those and you start heating it. And then as you start heating it, I forgot the temperature you said, but it
About
becomes
100
plasma.
million. Yeah.
No, first it becomes.
First it becomes plasma. So it's a gas, and then
Yeah.
it turns into a plasma at about 10,000 degrees.
And then so you have a bunch of electrons and ions flying around, and then you keep heating the thing.
Yep.
And I guess as you heat the thing, the ions hit each other rarer and rarer.
Yes.
So, oh man, that's not fun. So you have to keep
Yes.
heating it, such that you have to keep hitting it until the probability of them colliding becomes reasonably high.
And so
also on top of that, and sorry to interrupt, you have to prevent them from hitting the walls of the reactor.
Yes, exactly.
Somehow.
So you asked about the definitions of the requirements for fusion. So the most famous one, or some sense the most intuitive one, is the temperature. And the reason for that is that you can make many, many kinds of plasmas that have zero fusion going on in them. And the reason for this is that the average, so you can make a plasma at around 10,000. In fact, if you come, by the way, you're welcome to come to our laboratory at the PSFC. I can show you a demonstration of a plasma that you can see with your eyes, and it's at about 10,000 degrees, and you can put your hand up beside it and all this, and it's like, and nothing, there's zero fusion going on.
So you have, sorry, what was the temperature of the plasma?
About 10,000 degrees.
You can stick your hand in?
Well, you can't stick your hand into it, but there's a glass tube. You can basically see this with your bare eye. Yeah. And you can put your hand on the glass tube because it's...
What's the color? Is it purple?
It's purple, yeah.
Blue and purple.
It's blue and purple. It is kind of beautiful. Plasmas are actually quite astonishing sometimes in their beauty. Actually, one of the most amazing forms of plasma is lightning, by the way, which is an instantaneous form of plasma that exists on Earth, but immediately goes away because everything else around it is at room temperature.
That's fascinating.
Yeah, so there's different requirements in this. So making a plasma takes about this, but at 10,000 degrees, even at 1,000,000 degrees, there's almost no probability of the fusion reactions occurring. And this is because while the charged particles can hit into each other, if you go back to the very beginning of this, remember I said, these charged particles have to get to within distances which are like this size of a nucleus because of the strong nuclear force. Well, unfortunately, as the particles get closer, the repulsion that comes from the charge, the Coulomb force, increases like the inverse distance squared.
Oh, no.
So as they get closer, they're pushing harder and harder apart. So then it gets a little bit more exotic, which maybe you'll like, though, that it turns out that people understood this at the beginning of the age of after Rutherford discovered the nucleus. It's like, it's like, how is this going to work, right? Because how do you get anything within these distances? It's like, inquire extraordinary energy, and it does. And in fact, when you look at those energies, they're very, very high. But it turns out quantum physics comes to the rescue, because the particles aren't actually just particles. They're also waves. This is the point of quantum, right? You can treat them both as waves and as particles. And it turns out if they get in close enough proximity to each other, then the particle pops through basically this energy barrier through an effect called quantum tunneling, which is really just the transposition of the fact that it's a wave so that it has a finite probability of this. It's this, by the way, you talk about like, do you have a hard time like conceptualizing this? This is one of them.
Quantum tunneling is one of them?
Yeah, this is like throwing a ping pong ball like at a piece of paper, and then every 100 of them just like magically show up on the other side of the paper without seemingly breaking the paper. I mean, to use a physical analogy.
And that phenomena is critical for the function of nuclear fusion.
Yes, for all kinds of fusion. So this is the reason why stars can work as well too. Like the stars would have to be much, much hotter actually to be able to. In fact, it's not clear that they would actually ignite. In fact, without this effect. Anyway, so we get to that. So this is why there's another requirement. It's not, so you must make a plasma, but you also must get it very hot in order for the reactions to have a significant probability to actually fuse. Mm-hmm. And it actually falls effectively almost to zero for lower temperatures as well too.
So there's some nice equation that gets you to 50 million degrees, or like you said, practically speaking, 100 million.
So it's a really simple equation. It's the ideal gas law, basically, almost. So in the end, you've got a certain number of these fusion particles in the plasma state. They're in the plasma state. There's a certain number of particles. And if the confinement is perfect, if you put in a certain content of energy, then basically eventually they come up in a temperature and they go up to high temperature. This turns out to be, by the way, extraordinarily small amounts of energy. And you go, what? It's like I'm getting something to like 100 million degrees. That's going to take the biggest flame burner that I've ever seen. No. And the reason for this is it goes back to the energy content of this. So yeah, you have to get it to high average energy, but there's very, very few particles.
This is low density. How
It's
do you
low
get it to
density.
be low density in a reactor? Is this
So the way that you do this is primarily, again, this is not exactly true in all kinds of fusion, but in the primary one that we work on, magnetic fusion, this is all happening in a hard vacuum. So it's like it's happening in outer space. So basically, you've gotten rid of all the other particles except for these specialized
so you
fuel
add
particles.
them one at a time? then-
No, actually, it's even easier than that. You connect a gas valve, and you basically leak gas into it.
In a controlled fashion?
Yeah, yeah.
Well, this
Yeah.
is beautiful. How do
It's
you
a gas cylinder.
How do you get it from hitting the walls?
Yeah. So now you've touched on the other necessary requirements. So it turns out it's not just temperature that's required. You must also confine it. So what does this mean? Confine it.
And there's two types of confinement, as you mentioned. You
Yeah.
mentioned the magnetic one.
Magnetic one, and there's the one called inertial as well too. But the general principle actually has nothing to do with, in particular, with what the technology is that you use to confine it. It's because this goes back to the fact that the requirement in this is high temperature and thermal content. So it's like building a fire. Right? And what this means is that when you release the energy into this or apply heat to this, if it just instantly leaks out, it can never get hot, right? So you're familiar with this, is like if you've got something that you're trying to apply heat to, but you're just throwing the heat away very quickly. This is why we insulate homes, by the way, and things like this, right? It's like you don't want the heat that's coming into this room to just immediately leave, because you'll just start consuming infinite amounts of heat to try to keep it hot. So in the end, this is one of the requirements, and it actually has a name. We call it the energy confinement time. So this means if you release a certain amount of energy into this fuel, kind of how long you sit there and you look at your watch, how long does it take for this energy to like leave the system? So you could imagine that in this room that, these heaters are putting energy into the air in this room, and you waited for a day, would all the heat have gone to outside if I open up the windows? That's energy confinement time. Okay, so it's the same concept as that. So this is an important one. So all fusion must have confinement. There's another more esoteric reason for this, which is that people often confuse temperature and energy. So what do I mean by that? So this is literally a temperature, which means that it is a system in which all the particles, every particle, has high kinetic energy and is actually in a fully relaxed state, namely that entropy has been maximized. That gets a little bit more technical, but this means that basically it is a thermal system. So it's like the air in this room, it's like the water, it's the water in this. These all have temperatures, which means that there's a distribution of those energies because the particles have collided so much that it's there. So this is distinguished from having high energy particles, like what we have in like particle accelerators like CERN and so forth. Those are high kinetic energy, but it's not a temperature, so it actually doesn't count as confinement. So we go through all of those. You have temperature, and then the other requirement, not too surprising, is actually that there has to be enough density of the fuel.
Enough, but not too much.
Enough, but not too much, yes. And so in the end, the way that there's a fancy name for it, it's called the Lawson criterion, because it was formulated by scientists in the United Kingdom about 1956 or 1957. And this was essentially the realization of, this is what it's going to take, regardless of the confinement method. This is the basic, what it is actually power balance. It just says, there's a certain amount of heat coming in, which is coming from the fusion reaction itself, because the fusion reaction heats the fuel, versus how fast you would lose it. And it basically is summarized by those three parameters, which is fairly simple. So temperature, and the reason we say 100 million degrees is because almost always in And for this kind of fusion, deuterium-tritium fusion, the minimum in the density and the confinement time product is at about 100 million. So you almost always design your device around that minimum. And then you try to get it contained well enough, and you try to get enough density. So, so that temperature thing sounds crazy, right? That's what we've actually achieved in the laboratory. Like our experiment here at MIT, when it ran at its optimum configuration, it was at 100 million degrees.
Mhm.
But it wasn't actually the product of the density and the confinement time wasn't sufficient that we were at a place that we were getting high net energy gain, but it was making fusion reactions. So this is the sequence that you go through. Make a plasma, then you get it hot enough. And when you get it hot enough, the fusion reactions start happening so rapidly that it's overcoming the rate at which it's leaking heat to the outside world. And at some point, it just becomes like a star, like a sun. And our own sun and a star doesn't have anything plugged into it. It's just keeping itself hot through its own fusion reactions. In the end, that's really close to what a fusion power plant would look like.
What does it visually look like? Does it look like you said, like purple plasma?
Yeah, actually, it's invisible to the eye because it's so hot that it's basically emitting light in frequencies that we can't detect. It's invisible. In fact, light goes through it. Visible light goes through it so easy that if you were to look at it, what you would see in our own particular configuration, what we make is in the end is a donut-shaped. It's a vacuum vessel to keep the air out of it. And when you turn on the plasma, it gets so hot that most of it just disappears in the visible spectrum. Mm-hmm. You can't see anything. And there's very, very cold plasma, which is between 10 and 100,000 degrees, which is out in the very periphery of it, which is so the very cold plasma is allowed to interact with has to interact with something eventually at the boundary of the vacuum vessel. And this kind of makes a little halo around it, and it glows this beautiful purple light, basically. And that's what we can sense in the human spectrum. Yeah.
I remember reading on a subreddit called Shower Thoughts, which people should check out. It's just fascinating philosophical ideas that strike you while you're in the shower. And one of them was, it's lucky that fire, when it burns, communicates that it's hot using visible light. Yeah. Otherwise, humans would be screwed. Yeah. I don't know if there's a deep, profound truth to that, but nevertheless, I did find it on Shower Thoughts subreddit.
Actually, I do have this goes off on a bit of. You're right. This is actually, it's interesting because as a scientist, you also think about evolutionary functions and how we got, like, why do we have the senses that we do? It's an interesting question, right? Like, why can bees see in the ultraviolet and we can't? Then you go, well, it's natural selection. For some reason, this wasn't really particularly important to us, right? Mm-hmm. Why can't we see in the infrared and other things can? It's like,
Because the people that could.
It's a fascinating question, right? Obviously, there's some advantage that you have there that isn't there, and even color distinguishing, right, of something safe to eat, not safe, whatever it would be. I actually go back to this because it's something that I tell all of my students when I'm teaching ionizing radiation and radiological safety. Whatever you say, there's a cultural concern, or that when people hear the word radiation, like, what does this mean? It literally just means light, is what it means, right? But it's light in different parts of the spectrum, right? And so it turns out, besides the visible light that we can see here, we are immersed in almost the totality of the electromagnetic spectrum. There is visible light, there's infrared light, there is microwaves going around us. That's how our cell phone works. It's way past our detection capability. But also higher energy ones, which have to do with ultraviolet light, how you get a sunburn, and even X-rays and things like this at small levels are continually being, like, from the concrete in the walls of this hotel. There's X-rays hitting our body continuously. I can bring out we can go down to the lab at MIT. I can bring out a detector and show you. Every single room will have these.
By our body, you mean the 10 to the 28 atoms?
Yeah, the 10 to the 28 atoms, and they're coming in and they're interacting with those things. And those, particularly the ones where the light is at higher average energy per light particle, those are the ones that can possibly have an effect on human health. So we have, it's interesting, humans and all animals have evolved on Earth where we're immersed in that all the time.
Yeah.
There's natural sources of radiation all the time, yet we have zero ability to detect it, like zero.
Yeah, and our cognitive ability to filter it all out and not.
It would
not
probably overwhelm us, actually, if we could see all of it. But my main point goes back to your thing about fire and self-protection. If if ionizing radiation was such a critical aspect of the health of organisms on Earth, we would almost certainly have evolved methods to detect it, and we have none. Anyway, yes.
The physical world that's all around is
Yes.
just incredible. You're blowing my mind, Dr. Dennis Whyte. Okay, so you have experience with magnetic confinement. You have experience with inertial confinement. Most of your work has been in magnetic confinement.
Yes,
But let's sort of talk about the sexy recent thing for a bit of a time. There's been a breakthrough in the news that laser-based inertial confinement was used by DOE's National Ignition Facility at the Lawrence Livermore National Laboratory. Can you explain this breakthrough that happened in December?
Yeah. So it goes to the set of criteria that I talked about before about getting high energy gain. So in the end, what are we after in fusion is that we basically assemble this plasma fuel in some way, and we provide it a starting amount of energy. Think of lighting the fire. And what you want to do is get back like significant excess gain from the fact that the fusion is making more, is releasing the energy. So it's like the equivalent of like, we want to have a small match, light a fire, and then the fire keeps us hot. It's like this is very much like that. So as I said, we've made many of the, and what do I mean by we? It's like the fusion community has pursued aspects of this through a variety of different confinement methodologies. Is that the key part about what happens? So what was the threshold we had never gotten over before was that if you only consider the plasma fuel, not the total engineering system, but just the plasma fuel itself, we had not gotten to the point yet where basically the size of the match was smaller than the amount of energy that we got from the fusion.
Is there a good term for when the output is greater than the input?
Yes, there is. Well, there's several special definitions of this. So one of them is that if you like in a fire, if you light a match and you have it there and it's an infinitesimal amount of energy compared to what you're getting out of the fire, we call this ignition, which makes sense, right? This is like what our own sun is as well too. So that was not ignition in that sense as well too. So what we call this is scientific, the one that I just talked about, which is for some instance, when I get enough fusion energy released compared to the size of the match, we call this scientific break-even. Break-even. And it's because you've gotten past the fact that this is unity now at this point.
What is fusion gain, or as using the notation Q from the paper overview of the SPARC tokamak, before we talk, using just the same kind of term?
Yeah, actually, so the technical term is Q, capital Q.
Oh, so people actually use Q.
We actually use capital Q, or sometimes it's called
Q is taken.
Q sub P or something like this. Okay, so this is... Which means what it means is that it's in the plasma. So all we're considering is the energy balance or gain that comes from the plasma itself. We're not considering the technologies which are around it, which are providing the containment and so forth. So why the excitement and so? Well, because for one reason, it's a rather simple threshold to get over to understand that you're getting more energy out from the fusion, even a theoretical sense, than you were from the starting match.
Do you mean conceptually simple?
It's conceptually simple that you get past one, that everyone like when you're less than one, that's much less interesting than getting past one, because
so there's really the big
you start to get energy gain,
to get past.
But it really is a scientific threshold, because what QP actually denotes is the relative amount of self-heating that's happening in the plasma. So what I mean by this is that in the end, in these systems, what you want is something where the relative amount of heating, which is keeping the fuel hot, is dominated from the fusion reactions themselves. And so it becomes, it's sort of like thinking like a bonfire is a lot more interesting physically than just holding a blowtorch to a wet log, right? There's a lot more dynamics. It's a lot more self-evolved and so forth. And what we're excited as scientists is that it's clear that in that experiment that they actually got to a point where the fusion reactions themselves were actually altering the state of the plasma. It's like, wow. I mean, we'd seen it in glimpses before in magnetic confinement at relatively small levels, but apparently it seems like in this experiment, it's likely to be a dominated by self-heating. That's a very important, that's a very
So that
interesting
makes it a
sign.
self-sustaining type of
It's
reaction.
more self-sustaining, it's more self-referential system in a sense, and it sort of self-evolves in a way. Again, it's not that it's going to evolve to a dangerous state, it's just that we want to see what happens when the fusion is the dominant heating source.
And we'll talk about that. But
Yeah.
so there's also another element, which is the inertial confinement. Laser-based inertial confinement is kind of a little bit of an underdog. So a lot of the broad nuclear fission community has been focused on magnetic confinement. Can you explain just how laser-based inertial confinement works? So it says 192 laser beams were aligned on a deuterium tritium DT target smaller than a pea.
Yes.
This is like
BB actually. Yeah.
okay. Well, it depends. Not all peas are made the same, but this is like throwing a perfect strike in baseball from a pitch. This is like a journalist wrote this, I think. This is like, oh no, it's not a journalist. It's DOE wrote.
Yeah, it could
Department
be,
of Energy.
We try to use all these analogies.
This is like throwing a perfect strike in baseball from a pitcher's mound 350 miles away from the plate. There you go. Department of Energy. The United States Department of Energy wrote this. Okay. Can you explain
Interesting
what the lasers
what actually happens? Yeah. Actually, there's usually mass confusion about this. So what's going on in this form of energy? So the fuel is delivered in a discrete, the fusion fuel, the deuterium and tritium, is in a discrete spherical. It's more like a BB. Let's call it a BB. So it's a small one, and all the fuel that you're going to try to burn is basically there. Okay, and it's about that size. So so how are you going to get? And it's at literally it's like at 20 degrees above absolute zero, because the deuterium and tritium are kept in a liquid and solid state.
Oh,
so
wow! So the fuel is injected not as a gas, but as a solid.
It's actually, and it's very, and in these particular experiments, they can introduce one of these, these targets once per day, approximately, something like that, because it's kind of amazing technology, actually, that I know some of the people that worked on this back in the day they actually make these things at a BB size of this frozen fuel. It's actually at cryogenic temperatures, and they're almost like smooth to the atom level. I mean, they're amazing pieces of technology. So what you do in the end is what you have is a spherical assembly of this fuel, like a ball. And what is the purpose of the lasers? The purpose of the lasers is to provide optical energy to the very outside of this. And what happens is that energy is absorbed because it's in the solid phase of matter, so it's absorbed really in the surface. And then what happens is that when it's absorbed in something called the ablator, what does that mean? It means it goes instantly from the solid phase to the gas phase. So it becomes like a rocket engine. But you hit it like very uniformly. So there's like rocket engines coming off the surface. Think of like an asteroid almost, where there's like rockets coming off all this thing. So what does that do? Well, what does a rocket do? It actually pushes, by Newton's laws, right? It pushes the other thing on the other side of it, equal and opposite reaction. It pushes it in. So what it does is that the lasers actually don't heat. This is what was confusing. People think the lasers, we're going to get it to 100 million degrees. In fact, you want the exact opposite of this. What you want to do is get essentially a rocket going out like this. And then what happens is that the sphere, and this is happening in a billionth of a second or less, actually, this rapidly, that force, so rapidly compresses the fuel that what happens is that you're squeezing down on it and it's like, what was BB that's bad, actually. BB, I should have started with a basketball. Goes from like a basketball down to something like this, in a billionth of a second. And when that happens, I mean, you scale that in your mind. So when that happens, and in this comes from almost from classical physics, so there's some quantum in it as well too. But basically, if you can do this like very uniformly and so-called adiabatically, like you're not actually heating the fuel, what happens is that you get adiabatic compression, such that the very center of this thing all of a sudden just spikes up in temperature, because it's actually done so fast So why is it called inertial fusion? It's because you're doing this on such fast timescales that the inertia of the hot fuel basically is still finite, so it can't like push itself apart before the fusion happens.
Oh wow.
Yeah.
So how do you make it so fast?
This is why you use lasers, because you're applying this energy in very, very short periods of time, like under a fraction of a billionth of a second. And so basically that, and then the force which is coming from this comes from the energy of the lasers, which is basically the rocket action, which does the compression.
So is the force, is the inward facing force,
Is
that increasing the temperature
no,
exponentially?
you want to keep the fuel cold and just literally just ideally compress it. And then in something which is at the very center of that compressed sphere, because you've compressed it so rapidly, the laws of physics basically require for it to increase in temperature.
So the
effect is like, if you know the thing, so adiabatic cooling we're actually fairly familiar with. If you take a spray can, right, and you push the button, when it rapidly expands, it cools. This is the nature of a lot of cooling technology we use, actually. Well, the opposite is true, that if you would take all of those particles and jam them together very fast back in, they want to heat up. And that's what happens. And then what happens is you basically have this very cold, compressed set of fusion fuel. And at the center of this, it goes to this 100 million degrees Celsius. And so if it gets to that 100 million degrees Celsius, the fusion fuel starts to burn. And when that fusion fuel starts to burn, it wants to heat up the other cold fuel around it. And it just basically propagates out so fast that what you would do, ideally, you would actually burn, in a fusion sense, most of the fuel that's in the pellet. So this was very exciting, because what they had done was, it's clear that they propagated this, they got this, what they call a hot spot, and in fact that this heating had propagated out into the fuel, and that's the science behind inertial fusion.
So the idea behind a reactor that's based on this kind of inertial confinement is that you would have a new BB every like
10 times a second or something like that.
And that there's some kind of, so there's a incredible device that you kind of implied that kind of has to create one of those BBs.
So you have to make the BBs very fast. There's reports on this, but about what does it mean? The starting point is, can you make this gain? So this was a scientific achievement primarily, because
and the rest is just engineering.
No. The rest is incredibly complicated engineering. Well, in fact, there's still physics hurdles to overcome. So where does this come from? And it's actually because if you want to make an energy source out of this, this had a gain of around 1.5. That, namely, the fusion energy was 1.5 times the laser input energy. Okay, this is a fairly significant threshold. However, from the science of what I just told you, is that there's two fundamental efficiencies which come into it, which really come from physics, really. One of them is hydrodynamic efficiency. What I mean by this is that it's a rocket. So this just has a fundamental efficiency built into it, which comes out to orders of like 10%. So this means is that your ability to do work on the system is just limited by that, okay? And then the other one is the efficiency of laser systems themselves, which if their wall plug efficiency is 10%, you've done spectacularly well. In fact, the wall plug efficiency of the ones using that experiment are more like 1%, right? So when you go through all of this, the approximate, place that you're ordering this is for a fusion power plant would be a gain of 100, not 1.5. So you still, and hopefully we see experiments that keep climbing up towards higher and higher gain. But then the whole fusion power plant is a totally different thing. So it's not one BB and one laser pulse per day. It's like 5 or 10 times per second. Like like that, right? So you're doing it there. And then comes the other aspect. So it's making the targets, delivering them, being able to repeatedly get them to burn. And then we haven't even talked about how do you then get the fusion energy out, which is mainly because these things are basically micro implosions which are occurring. So this energy is coming out to some medium on the outside that you've got to figure out how to extract the energy out of this thing.
How do you convert that energy to electricity?
So in the end, you have to basically convert it into heat in some way. So most of what fusion makes mostly is very energetic particles from the fusion reaction. So you have to slow those down in some way and then make heat out of it. So basically the conversion of the kinetic energy of the particles into heating some engineered material that's on the outside of this.
And that's from a physics perspective is a somewhat solved problem, but from an engineering is still wide open.
Physics. I can show you all the equations that tell you about how it slows down and converts kinetic energy into heat, and then what that heat means. You can write out like an ideal thermal cycle, like a Carnot cycle. So the physics of that, great. The integrated engineering of this is a whole other thing.
I'll ask you to maybe talk about the difference between inertial and magnetic, but first we'll talk about magnetic. But let me just linger on this breakthrough. It's nice to have exciting things, but in a deep human sense, there's no competition in science and engineering. We're all, like you said, we're broad. First of all, we are humanity altogether. And you talk about this, it's a bunch of countries collaborating. It's really exciting. There's a nuclear fusion community broadly, but then there's also MIT. There's colors and logos, and it's exciting. And you have friends and colleagues here that work extremely hard and done some incredible stuff. Is there some sort of how do you feel seeing somebody else get a breakthrough in using a different technology? Is that exciting? Does the competitive fire get
all of the above? I mean,
the ignition.
I have to wave the flag a little bit. So MIT was a central player in this accomplishment. Interesting, I would say it showed some of our two best traits. So one of them was that how do you know that this happened? This measurement, right? So one of the ways to do this is, if I told you, is that in the DT fusion, what it actually, the product that comes out is helium. We call it an alpha, but it's helium, and a free neutron, right? So the neutron contains 80% of the fusion of the energy released by the fusion reaction, and it also, because it lacks a charge, it basically tends to just escape and go flying out. So this is what we would use eventually for. That's mostly what fusion energy would be. But so what my colleagues, my scientific colleagues at the Plasma Science and Fusion Center built were extraordinary measurement tools of being able to see the exact details of not only the number of neutrons that were coming out, but actually what energy that they're at. And by looking at that configuration, it reveals enormous. I'm not gonna scoop them because they need to publish the paper, but it reveals enormous amounts of scientific information about what's happening in that process that I just described. So exciting. I mean, and I have colleagues there that have worked for 30 years on this for that moment. Of course you're excited for them. I mean, and there's one of those, there is nothing, it's hard to describe to people who it's almost addicting to be a scientist when you get to be at the forefront of research of anything. When you see an actual discovery of some kind and you're looking at it, particularly when you're the person who did it, right? And you go, no human being has ever seen this or understood this. It's pretty thrilling, right? So even in proxy, it's incredibly thrilling to see this. It's not, I don't know, it's rivalry or jealousy. It's I can tell you already, fusion is really hard. So anything that keeps pushing the needle forward is a good thing. But we also have to be realistic about what it means, to making a fusion energy system. Yeah. That's
and then, but that's the fun. I mean, these are still the early steps. Maybe you can say the early leaps. So let's talk about the magnetic confinement. How does magnetic confinement work? What's the tokamak? How does it all work?
So go back to that. So why inertial confinement works on the same principle that a star works. So what is the confinement mechanism in the star is gravity, because it's its own inertia of the something the size of the sun basically pushes literally a force by gravity against the center. So the center is very, very hot, 20 million degrees, and literally outside the sun, it's essentially zero because it's vacuum of space. How the hell does that do that? It does that and it's out of thermal. Why doesn't it just leak all of its heat? It doesn't leak its heat because it all is held together by the fact that it can't escape because of its own gravity. So this is why the fusion happens in the center of the star. We think of the surface of the sun as being hot. That's the coldest part of the star. So of our own sun, this is about in 5,500 degrees. A beautiful symmetry, by the way. So how do we know all this? Because We can't, of course, see directly into the interior of the sun. By knowing the volume and the temperature of the surface of the sun, you know exactly how much power it's putting out. And by this, you know that this is coming from fusion reactions occurring at exactly the same rate in the middle of the sun.
Is it possible, as a small tangent, to build an inertial confinement system like the sun? Is it possible to create a sun?
It is, of course, possible to make a sun, otherwise you wouldn't have stars. But it is not possible on Earth because, for the simple reason that it takes the gravitational force is extremely weak, and so it takes something like the size of a star to make fusion occur in the center.
Well, I didn't mean on Earth. I mean, if you had to build like a second sun, how'd you do it?
You can't. There's not enough hydrogen around. Yeah.
So the limiting factor is just the hydrogen.
Yeah, I mean the forces and energy that it takes to assemble that is just mind-boggling.
All right.
So we wouldn't do that.
To be continued.
Yeah, to be continued. So what are we doing it with? So in the one that I just described, it's like you say, so you have to replace this with some force which is better than that. And so what I mean by that is it's stronger than that. So what I talked about, the laser fusion, this is coming from the force, which is enormous compared to gravity, like from the rocket action of pushing it together. So in magnetic confinement, we use another force of nature, which is the electromagnetic force. And it's orders and orders of magnitude stronger than the gravitational force. And the key force that matters here is that if you have a charged particle, that namely it's a particle that has an net electric charge, and it's in the proximity of a magnetic field, then there is a force which is exerted on that particle. So it's called the Lorentz force for those who are keeping track. So that is the force that we use to replace physical containment. So this again confused. How do you hold something at 100 million degrees? It's impossible in a physical container. This is not like, it's not this plastic bottle holding in this liquid or a gas chamber. What you're doing is you're immersing the fuel in a magnetic field that it basically exerts a force at a distance. This comes back again like why plasmas are so strange. It's the same thing here. And if it's immersed in this magnetic field, you're not actually physically touching it, but you're making a force go onto it. So that's the inherent feature of magnetic confinement. And then magnetic confinement devices are like a tokamak, are basically configurations which exploit the features of that magnetic containment. There's several features to it. One is that the stronger the strength of the magnetic field, the stronger the force. And for this reason is that if you increase the strength of magnetic fields, this means that the containment, because namely the force which you're pushing against it, is more effective. And the other feature is that there is no force. So for those who remember magnetic fields, what are these things? They're also invisible. But if you think of permanent magnets or your fridge magnet, there are field lines which we actually designate as arrows, which are going around. You sometimes see this in school when you have the iron filings on a thing and you see the directions of the magnetic field lines, or when you use a compass, right? So that's telling you north, because we're living in an immersed magnetic field made by the Earth, which is at very low intensity magnetic, but it's strong enough that we can actually see what direction it is. So this is the arrow that the magnetic field is pointing. It's always pointing north. And for us, so an interesting feature of this force is that there is no force along the direction of the magnetic field. There's only force in the directions orthogonal to the magnetic field. So this, by the way, is a huge deal in a whole other discipline of plasma physics, which is like the study of like our near atmosphere. So the study of aurora borealis, what's happening in the near atmosphere, what happens when solar flares hit the magnetic field. In fact, remember I said fusion is the reason that life is responsible in the universe? Well, you could also argue so is magnetic confinement, because the charged particles which are being emitted from the galaxy and from our own star would be very, very damaging on Earth. So we get two layers of protection. One is the atmosphere itself, but the other one is the magnetic field which surrounds the Earth and basically traps these charged particles so they can't get away. It's the same deal.
How do you create a strong magnetic field?
Yeah. So
with a giant magnet.
Yeah. So it's basically true.
Engineering is
there's
awesome.
essentially two ways to create a magnet. So one of them is that we're familiar with, like fridge magnets and so forth. These are so-called permanent magnets. And what it means is that within these, the atoms arrange in a particular way that it produces, the electrons basically arrange in a particular way that it produces a permanent magnetic field that is set by the material. So those have a fundamental limitation how strong they can be, and they also tend to have this like circular shape like this. So we don't typically use those. So what we use are so-called electromagnets. And what is this? It's like so the other way to make a magnetic field, also go back to your elementary school physics or science class, is that you take a nail and you wrap a copper wire around it and connect it to a battery, then it can pick up iron filings. This is an electromagnet. At its simplest, what it is, it's an electric current which is going in a pattern around and around and around. And what this does is it produces a magnetic field which goes through it by the laws of electromagnetism. So that's what that's how we make the magnetic field in these configurations. And the key there is that it's not limited by the magnetic property of the material. The magnetic field amplitude is set by the amount of the geometry of this thing and the amount of electric current that you're putting through. And the more electric current that you put through, the more magnetic field that you get. The closest one that people maybe see is one of my favorite skits actually was Super Dave Osborne on, it's probably past you, it was like in a show called Bizarre. Super Dave Osborne, which was a great comedian he was a stunt man, and one of his tricks was that he gets into a car, and then one of those things in the junkyard comes down, and picks up the car and then puts it into the crusher. This is his stunt, which is pretty hilarious. Anyway, but that thing that picks him up, like, how does that work? That's actually not a permanent magnet. It's an electromagnet. And so you can by turning off and on the power supply, it turns off and on the magnetic field. So this means you can pick it up, and then when you switch it off, the magnetic field goes away and the car drops. Okay, so that's what it looks like.
Speaking of giant magnets, MIT and Commonwealth Fusion Systems, CFS, built a very large, high-temperature superconducting electromagnet that was ramped up to a field strength of 20 Tesla, the most powerful magnetic field of its kind ever created on Earth. Because I enjoy this kind of thing, can you please tell me about this magnet?
Yeah, sure. It's fun. Yeah, there's a lot to parse there. So maybe we already explained an electromagnet, which in general is what you do is you take electric current and you force it to follow a pattern of some kind, typically like a circular pattern, around and around and around and around it goes. And the more current and the more times it goes around, the stronger the magnetic field that you make. Okay. And as I pointed out, it's like really important in magnetic confinement because it is the force that's produced by that magnet. In fact, technically it goes like the magnetic field squared because it's a pressure which is actually being exerted on the plasma to keep it contained.
Just so we know, for magnetic confinement, what is usually the geometry of the magnet? What are we supposed to imagine?
Yeah, so the geometry is typically is what you do is you want to produce a magnetic field that loops back on itself. And the reason for this goes down to the nature of the force that I described, which is that there's no containment or force along the direction of the magnetic field. Right. So here's a magnetic field. In fact, what it's more technically or more graphically, what it's doing is that when the plasma is here, here's plasma particles here. Here's a magnetic field. What it does is it forces all those, because of this Lorentz force, it makes all of those charged particles execute circular orbits around the magnetic field. And they go around like this, but they stream freely along the magnetic field line. So this is why the nature of the containment is that if you can get that circle smaller and smaller, it stays further away from Earth temperature materials. That's why the confinement gets better. But the problem is that because it free streams along, so if we just have a long straight magnetic field, okay, it'll just keep leaking out the ends like really fast. So you get rid of the ends. So you basically loop it back around. So what these look like are typically donut-shaped, or more technically toroidal-shaped, but donut-shaped things where this collection of magnetic fields loops back on itself, and it also, for reasons which are more complicated to explain, basically it also twists slowly around in this direction as well too. So that's what it looks like. That's what the plasma looks like, because that's what the fuel looks like. So then this means is that the electromagnets are configured in such a way that it produces the desired magnetic fields around this. So
How precise does this have to be?
you were probably listening to our conversation with some of my colleagues yesterday. So it's actually, it depends on the configuration about how you're doing it.
The configuration of the plasma.
The configuration of the electromagnets and about how you're achieving this requirement. It's fairly precise, but it doesn't have to be, particularly in something like a tokamak. What we do is we produce planar coils, which just mean they're flat, and we situate them. So if you think of a circle like this, what does it produce? If you put current through it, it produces a magnetic field which goes through the circle like this. So if you align many of them like this, there's things online. You can go see the picture. You keep arranging these around in a circle itself. This forces the magnetic field lines to basically just keep executing around like this. So you tend to align. That one tends to, it requires good good alignment. It's not like insane alignment because you're actually exploiting the symmetry of the situation to help it. There's another kind of configuration of this kind of magnetic confinement called a stellarator, which is we have these names for historic reasons.
Which is different than a tokamak.
It's different than a tokamak, but actually works on the same physical principle. That namely, in the end, it produces a plasma which loops in magnetic fields, which loop back on themselves. But in that case, the totality of the confining magnetic field is produced by external three-dimensional magnets, so they're twisted. And it turns out the precision of those is more stringent. Yeah.
So are tokamaks by far more popular for research and development currently than stellarators?
Of the concepts which are there, the tokamak is by far the most mature in terms of its breadth of performance and thinking about how it would be applied in a fusion energy system. And the history of this was that in fact, you asked about, if we go back to the history of the Plasma Science and Fusion Center, the history of fusion is that scientists had started to work on this in the 1950s. It was all hush-hush and, Cold War and all that kind of stuff. And it's like they realized, holy cow, this is like really hard. Like we actually don't really know like what we're doing in this, because everything was at low temperatures. They couldn't get confinement. It was interesting. And then they declassified it. And this is one of the few places that the West and the Soviet Union actually collaborated on, was the science
even
of this.
During the Cold War.
Even during the middle of the Cold War. It was really, and this actually perpetuates all the way to now. We can talk about the project that is sort of captured in now. But the reason they declassified it was because like everything like kind of like sucked basically, about trying to make this confinement in high temperature plasma. And then the Russians, then the Soviets, right, came along with this device called a tokamak, which is a Russian acronym, which basically means magnetic coils arranged in the shape of a donut. and they said, holy cow, like everyone was stuck at like a meager like 500,000 degrees or 500,000 degrees, which is like in fusion terms is zero basically. And then they come along and they say, oh, we've actually achieved a temperature 20 times higher than everybody else, and it's actually started to make fusion reactions. And everyone just go, oh, no way. It's just hype from this. It's like, there's no way, because we failed at this. It's a great story in the history of fusion is that then, but they insisted, said, no, look, you can see this from our data. It's like, this thing is really hot and it seems to be working. This is, late 1960s. And there was a team that went from the United Kingdom's Fusion Development Lab, and they brought this very fancy, amazing new technology called a laser. And they used this laser and they shot the laser beam like through the plasma, and by looking at the scattered light that came from it, they go that basically the scattered light gets more broadened in its spectrum if it gets hotter. So you could exactly tell the temperature of this, and even though you're not physically touching the plasma, it's like, holy cow, you're right, it is like it is 10 million degrees. And so this was one of those explosions of like, everyone in the world then wanted to build a tokamak, because it was clearly like, wow, this is like so far ahead of everything else that we tried before. So that actually has a part of the story to MIT and the Plasma Science and Fusion Center was, why is there a strong fusion and a major fusion program at MIT? It was because we were host to the Francis Bitter Magnet Laboratory, which is also the National High Field Magnet Laboratory. Well, you can see where this goes, right? From this, we're kind of telling the stories backwards almost, but the advent of a tokamak, along with the fact that you could make very strong magnetic fields with the technology that had been developed at that laboratory, that was the origins of sort of pushing together the physics of the plasma containment and the magnet technology and put them together in a way that I would say is, a very typical MIT success story, right? We don't do just pure science or pure technology. We sort of sit at this intersection between them. And there were several pioneers that of people at MIT, like Bruno Coppi, who's a professor in the physics department, and Ron Parker, who was a professor in electrical engineering and nuclear engineering. It's like even the makeup of the people, right, has got this blends of science and engineering in them. And that's actually was the origin of the Plasma Science and Fusion Center, was doing those things. So anyway, so back to this. So yes, tokamaks have achieved the highest in magnetic fusion by far, like the best amounts of these conditions that I talked about, and in fact pushed right up to the point where they were near QP of 1. Mm-hmm. They just didn't quite get over 1.
So can we actually just linger on the collaboration across different nations? Just maybe looking at the philosophical aspect of this. Even in the Cold War, there's something hopeful to me besides the energy, that these giant international projects are a really powerful way to ease some of the geopolitical tension, even military conflict across nations. There's a war in Ukraine and Russia. There's a brewing tension and conflict with China. Mm-hmm. Just the world is still seeking military conflict, cold or hot. What can you say about sort of the lessons of the 20th century in these giant projects in their ability to ease some of this tension?
So it's a great question. So as I said, there was a reason, because it was so hard. That was one of the reasons they declassified it, and actually they started working together in some sense on it as well too. And I think it was really, there was a heuristic or altruistic aspect to this. It's like, this is something that could change the future of humanity and its nature and its relationship with energy. Isn't this something that we should work on together? Mm-hmm. Right? And that went along in those ones. And in particularly, that any kind of place where you can actually have an open exchange of people who are sort of at the intellectual frontiers of your society, this is a good thing, right? Of being able to collaborate. I've had an amazing, career. I've worked with people from, it's like hard to throw a dart at a country and on the map and not hit a country of people that I've been able to work with. How amazing is that? And even just getting small numbers of people to bridge the cultural and societal divides is a very important thing. Even when it's a very teeny fraction of the overall populations, it can be held up as an example of that. But it's interesting that if you look at then that continued collaboration, which continues to this day, is that this actually played a major role, in fact, in East-West relations, or like Soviet-West relations. Is that back in the Reagan-Gorbachev days, which of course were interesting in themselves, of all kinds of changes happening, on both sides, right? But still, like a desire to, push down the stockpile of nuclear weapons and all that. Within that context, there was a fairly significant historic event that at one of the Reagan-Gorbachev summits, is that they had really they didn't get there. Like they couldn't figure out how to bargain to the point of some part of the treaty. I can't remember the details of it anymore. But they needed some kind of a symbol, almost, to say, but we're still going to keep working, towards something that's important for all of us. What did they pick? A fusion project. And that was in the mid-1980s. And actually, then after, so they basically signed an agreement that they would move forward to like literally collaborate on a project whose idea would be to show large net energy gain in fusion's commercial viability and work together on that. And very soon after that, Japan joined, as did the European Union. And now that project, it evolved over a long period of time and had some interesting political ramifications to it. But in the end, this actually also had South Korea, India, and China join as well too. So you're talking about like a major fraction of, and now Russia, of course, instead of the Soviet Union. And actually that coalition is holding together despite the obvious political, turmoil that's going around on all those things. And that's a project called ITER, which is under construction in the south of France right now.
Can you actually link it before we turn to the giant magnet and maybe even talk about SPARC and the stuff all amazing stuff going on at MIT? What is ITER? What is this international nuclear fusion mega project being built in the south of France?
So its scientific purpose is a worthy one, that it's essentially in any fusion device, the thing that you want to see is more and more relative amounts of self-heating. And this is something that had not been seen, although we had made fusion reactions and we'd seen small amounts of the self-heating, we never got to a dominant. This actually goes to this QP business, okay? The goal of ITER, and it shifted around a little bit historically, but fairly quickly became, we want to get to a large amount of self-heating. So this is why it has its primary feature is to get to QP of around 10. And through this is a way to study this plasma that has higher levels of self-determination around on it. But it also has another feature, which was, let's produce fusion power at a relevant scale. And actually they're linked together, which actually makes sense when you think about it, is that because the fusion power is the heating source itself, this means that they're linked together. And so ITER is projected to make about 500 million watts of fusion power. So this is a significant amount. Like this is what you would use, for powering cities.
So it's not just the research; it is the development of really trying to achieve scale here. So self-heating and scale.
Yeah. Yes. So this meant then too is the development of an industrial base that can actually produce the technologies like the electromagnets and so forth, and to do it with it is a tokamak. It is one of these, yes. But very interesting. It also revealed limitations of this as well too.
Like what?
Well, it's interesting is that it is clearly on paper and in fact in practice as well too. The world. And very different political systems, and you consider at least geopolitical or economic rivals or whatever you want to use, like working towards a common cause, and one that we all think is worthy is very like, okay, that's very satisfying. But it's also interesting to see the limitations of this. It's because, well, you've got 7, chefs in the kitchen. So what is this meant in terms of the speed of the project? And the ability to govern it and so forth, it's just been a challenge, honestly, around this. And this is, it's very hard technically what's occurring. But when you also introduce such levels of, this isn't just me saying it. There's like GAO reports from the U.S. government and so forth. It's hard to like steer all of this around. And what that's tended to do is make it, it's not the fastest decision-making process. My own personal view of it was interesting because you said about the magnet and Commonwealth fusion systems. I worked most of my career on ITER because when I came into the field in the early 1990s, when I completed my PhD and started to work, this was one of the most, like, you can't imagine being more excited about something. Like, we're going to change the world with this project. We're going to do these things. And we just poured like an entire generation and afterwards as well too, is just poured their imagination and their creativity about making this thing work. Very good. But also at some point though, when it got to being another 5 years of delay or a decade of delay, you start asking yourself, well, is this what I want to do? Mm-hmm. Right? Am I going to wait for this? So it was a part of me starting to ask questions with my students. I was like, is there another way that we can get to this extremely worthwhile goal, but maybe maybe it's not maybe it's not that pathway. And the other part that was clearly frustrating to me, because I'm an advocate of fusion. You asked me about I was like, well, it's laser fusion or inertial fusion or magnetic fusion. I just want fusion energy, okay? Because I think it's so important to the world. Is that? But the other thing, if that's the case, then why do we have only one attempt at it on the entire planet, which was ITER?
Mm-hmm.
It's like, that makes no sense to me, right? We should have multiple attempts at this with different levels of whatever you want to think about it, technical, schedule, scientific risk, which are incorporated in them. And that's going to give us a better chance of actually getting to the goal line.
With that spirit, you're leading MIT's effort to design SPARC, a compact, high-field DT burning tokamak. How does it work? What is it? What's the motivation? What's the design? What are the ideas behind it?
Yeah. At its heart, it's exactly the same concept as ITER. So it's basically a configuration of electromagnets. It's arranged in the shape of a donut. And within that, we would do the same thing that happens in all the other tokamaks, and including in ITER and in this one, is that namely you put in gas, make it into a plasma, you heat it up, it gets to about 100 million degrees. The differentiator in SPARC is that we use the actual deuterium-tritium fuel, and because of the access to very high magnetic fields, it's in a very compact space. It's very, very small. What do I mean by small? So it's 40 times smaller in volume than ITER.
Mm-hmm.
But it uses exactly the same physical principles. So this comes from the high magnetic field. So in the end, like, why does this matter? What it does is it does those things, and it should get to the point where it's producing over 100 million watts of fusion power. But remember, it's 40 times smaller. So ITER was 500 megawatts. Technically, our design is around 150 megawatts. So it's only about a factor of 3 difference, despite being 40 times smaller. And we see QP large, order of 10 or something like this. At that state is very important scientifically, because this is basically matches what ITER is looking to do. The plasma is dominated by its own heating. That's very, very important. And it does that for about 10 seconds. And the reason it's for 10 seconds is that in terms of that basically allows everything to settle in terms of the fusion in the plasma equilibrium. Everything is nice and settled. So you have seen the physical state at which you would expect a power plant to operate, basically for magnetic fusion. Like, wow, right? Mm-hmm. But it's more than that. And it's more than that. It's because about who's building it and why and how it's being financed. Mm-hmm. So that scientific pathway was made possible by the fact that we had access to a next generation of magnet technology. So to explain this real quick, why do we call it, you said it in the words, a superconducting magnet? What does this mean? Superconducting magnet means that the materials which are in the electromagnet have no electrical resistance. Mm-hmm. Therefore, when the electric current is put into it, the current goes around unimpeded. Mm-hmm. So it could basically keep going around and around, technically for infinity. And what that means, or for eternity. And what that means is that when you energize these large electromagnets, they're using basically zero electrical power to maintain them. Whereas if you would do this in a normal wire, like copper, you basically make an enormous toaster oven that's consuming enormous amounts of power and getting hot, which is the problem. That was the technical breakthrough that was realized by myself and, at the time, my students and postdocs and colleagues at MIT, was that we saw the advent of this new superconducting material, which would allow us to access much higher magnetic fields. It was basically a next generation of the technology, and it was quite disruptive to fusion. That, namely, what it would allow, that if we could get to this point where we can make around 20 Tesla, we knew by the rules of tokamaks that this is going to allow us to vastly shrink, like, the sizes of these devices. So it wouldn't take, although it's a worthy goal, it wouldn't take a 7-nation international, treaty basically to build it. You could build it with a company and a university.
So same kind of design, but now using the superconducting magnets.
Yeah, and if you look at it, it's If you just expand the size of it, they look almost identical to each other because it's based on and actually that comes for a reason, by the way, is that it also looks like a bigger version of the tokamak that we ran at MIT for 20 years, where we established the scientific benefits, in fact, of these higher magnetic fields. So that's the pathway that we're on. So we say, so what does this mean? The context is different because it's primarily being made by a private sector company spun out of MIT, because the way that it raised money and the purpose of the entity which is there is to make commercial fusion power plants, not just to make a scientific experiment. This is actually why we have that's why we have a partnership, right? Is that our purpose at MIT is not to commercialize directly, but boy, do we want to advance the technology and the science that comes along this. And that's the reason we're sort of doing it together.
So it's MIT and Commonwealth Fusion Systems.
Yeah.
So what's interesting to say about financing? And this seems like, from a scientific perspective, maybe not an interesting topic, but it's perhaps an extremely interesting topic. I mean, you can just look at the tension between SpaceX and NASA, for example.
Yes.
It's just clear that there's different financing mechanisms that can actually significantly accelerate the development of science and engineering.
It's great that you brought that up. We use several historic analogs, and one of them is around SpaceX, which is an appropriate one because space, putting things into orbit has a minimum size to it, and integrated technological complexity and budget and things like this. So, our point when we were like talking about starting like a fusion commercialization, company, people look at you like, isn't this still really just a science experiment? But one of the things that we pointed to was SpaceX to say, well, tell me like 25 years ago, how many people would have voted that, the leading entity on the planet to put things into orbit is a private company. Yeah. People would have thought you were not so, right? It's like, and what is interesting about SpaceX was that it proved it's more than actually just financing. It's really the purpose of the organization. So the purpose of and I'm not against public finance or anything like that, but the purpose of a public entity like NASA correctly, speaks to the political, because the cost comes from the political, assembly that is there, and I guess from us eventually as well too. But its purpose wasn't about like making a commercial product. It's about fundamental discovery and so forth, which is all really great. So like, why did SpaceX? It's interesting. Like, why did SpaceX succeed so well? Is because the idea was, it's like the focus that comes in the idea that you're going to relentlessly like reduce cost and increase efficiency is a drive that comes from the commercial aspect of it, right? And this also then changes the people in the teams which are doing it as well too, and in fact trickles throughout the whole thing, because the purpose isn't, while you're advancing things, like it's really good that we can put things in orbit a lot more cheaply. Like, it advances science, which is an interesting synergy, right? And it's the same thing that we think is going to happen in fusion. That namely, this is a bootstrap effect. That when you start to push yourself to think about near-term commercialization, it allows the science to get in hand faster, which then allows the commercialization to go faster, and up we go. By the way, we've seen this also in another. Again, you have to watch out with analogies, because they only can go so far. But like biotech is another one. Like, you look at the Human Genome Project, which was, it's sort of like, to me, that's like mapping the human genome is like that we can make net energy from fusion. Like, it's one of those like in your drawer that you go, this is a significant achievement by humanity, right, in this century. And there's the Human Genome Project, fully government funded. It's going to take 20, 25 years, because we basically know the technology. We're just going to be really diligent, keep going, and then all of a sudden, what comes along? Disruptive technology, right? You can sequence, shotgun sequencing and computer, recognition patterns, and basically, I can do this 100 times faster. Like, wow, right? And so that's really the. To me, that the story about why we launched Commonwealth Fusion Systems was more than just about another source of funding. which it is a different source of funding because it's also a different purpose, which is very important.
But there's also something about a mechanism that creates culture. So giving power to like a young student, ambitious student, to have a tremendous impact on the progress of nuclear fusion creates a culture that actually makes progress more aggressively. Like you said, when 7 nations collaborate, it gives more incentive to the bureaucracy to slow things down, to kind of let's first have a discussion, and certainly don't give voice to the young, ambitious minds that are really pushing stuff forward.
Yeah.
And there's something about like the private sector that rewards, encourages, inspires young minds to say in the most beautiful of ways "f you" to the to the boss.
Yeah,
just we'll make it faster, we'll make it simpler, we'll make it better, we'll make it cheaper.
Yeah. And sometimes that brashness doesn't bear out. That's an aspect that you just take a different risk profile as well too. But you're right. It's this, of the. I mean, it was interesting. Our own trajectory at the Fusion Center was like we were pushed into this place by necessity as well too, because I told you we had operated for a long time a tokamak on the MIT campus, achieve these world records like 100 million degree plasma and stuff. It's like, wow, this is fantastic. But somewhat ironically, I have to say, is that it was like, oh, but this isn't the future of fusion anymore. Like we're just going to stop with small projects because it's too small, right? So we need to really move on to these much bigger projects because that's really the future of fusion. And so it was defunded. And this basically put at risk, like we were going to essentially lose MIT in the ecosystem, really, of fusion, both from the research, but also clearly important from the educational part of it. So we pushed back against this. We got a lifeline. We were able to go, and it was in this time scale that we basically came up with this idea. It's like, we should do this. And in the end, it was all of those, the people who were in the C-level of the company were all literally students who got caught in that. They were PhD students at the time. So you talk about enabling another generation. It's like, yeah, there you go, right?
So SPARC gave
a lifeline.
Yeah. A lifeline gave fuel to the Fusion Center at MIT that it continues.
But it's way more than that. It wasn't just about like surviving for the sake of surviving. Yeah. It was like, in the end, for me, it became like this. I remember the moment. We talk about these moments as a scientist, and we were just like, we were working so hard about figuring out, like, will this really work? Like, and it's complex. Like, does the magnet work? Does the interaction with the plasma work? Does all these things work? And it was just a grind, push. And I remember the moment because I was sitting in my office in Brookline, and there was just like, I read like, and I was in, I don't know, whatever, the 20 or 40th slide or something into it. And it was sort of that moment, like it just came together. And I couldn't even sit down because all it was just like, my wife was like, why are you walking around the apartment like this? Like, I just couldn't, I said, it's going to work. Like, it's going to work. Like, holy cow. That moment of realization is like kind of amazing, but it also brings the responsibility of making it work as well.
Yeah, how do you make it work? Yeah. So you mean like that magic realization that you can have this modern magnet technology, and you can actually, like, why do we need to work with ITER? We can do it here.
Yeah. But it's interesting that ITER is that one of the reasons that we started with a group of 6 of us at MIT, and then once we got some funding through the establishment of the company, it became a slightly larger. But in the end, we had a rather small team. Like, this was like a team of order of like 20 to 25 people, design SPARC in like about 2 years. Right? How does that happen? Well, we're clever, but you have to give ITER its due here as well too. That, again, this is an aspect always of the bootstrap up. Like, I go back to the Human Genome Project. So modern day genomics would not be possible without the underlying basis that came from setting that up. It had to be there. It had to be curiosity-driven public program. It's the same with ITER, but because we had the tools that were there to understand ITER, we also had the tools to understand SPARC. So we parlayed those in an extremely powerful way to be able to tell us about what was going to happen. So these things are never simple, right? It's like people look at this, go, oh, this means we should we really have a public-based program about fusion, or should we have it all in the private? It's like, no, the answer is neither way, because in all these complex technologies, you have to keep pushing on all the fronts to actually get it there.
So The natural question when people hear breakthrough with the inertial confinement, with the magnetic confinement is, so when will we have commercial
Yeah.
reactors, power plants that are actually producing electricity? What's your sense, looking out into the future? When do you think you can envision a future where we have actual electricity coming from nuclear fusion?
Partly driven by us, but in other places as well too. So there's the advent. What's so different now than 3 or 4 years ago? Like we launched around 4 years ago. What's so different now is the advent of a very nascent but seemingly robust, like commercial fusion, endeavor. So it's not just Commonwealth Fusion Systems. There's something like 20 plus companies.
So there's a sector now.
There's a sector. They actually have something called the Fusion Industry Association, which
Nice.
if your viewers want to go see this describes the different, and they've got this plethora of approaches. Like I haven't even described all the approaches. I've basically described the mainline approaches. And they're all at varying degrees of technical and scientific maturity with very huge different, balances between them. But what they share is that because they're going out and getting funding from the private sector, is that their stated goals are about getting fusion into place so that both it meets the investors' demands, which are interesting, right, and the timescales of that, but also it's like, well, there's going to, and why? It's because it's easy. There's this enormous driver about getting carbon-free energy sources out into the market, and whoever figures those out is going to be it's going to be very important geopolitically, but also economically as well too. So it's a different kind of bet, I guess, or a different kind of gamble that you're taking with fusion, but it's so disruptive that it's like there's essentially a class of investors and teams that are ready to go after it as well too. So what do they share in this? They typically share getting after fusion on a time scale so that could it have any relevance towards climate change, battling climate change? And I would say this is difficult, but it's fairly easy because it's math. So what you do is you actually go to some target like 2050 or 2060, something like this, and say, I want to be blank percent of the world's market of electricity or something like that. And we know historically what it takes to evolve and distribute these kinds of technologies, because every technology takes some period of time. It's a so-called S curve. It's basically everything follows a logarithmic curve, like exponential type curve. It's a straight line, a log plot. And like you look at wind, solar, fission, they all follow the same thing. So it's easy. You take that curve and you go, that slope, and you work backwards. And you go, if you don't start in the early 2030s, like it's not going to have a significant impact by that time. So all of them share this idea. And in fact, it's not just the companies now. The US federal government has a program that was started last year that said we should be looking to try to get like the first, and what I mean by like, what does it mean to start? That you've got something that's putting electricity on the grid, a pilot, what we call it. And if that can get started like in the early 2030s, the idea of ramping it up, makes sense. And it's math, right? Yeah. So that's the ambition. Then the question is, and actually this is different because the government program, and they vary around in this. So for example, the United Kingdom's government idea was to get the first one on by 2040. And China has ambitions probably middle 2030s, or maybe a little bit later. And Europe, continental Europe, it's a little bit, I'm not exactly sure where it is, but it's like later. It's like 2050 or 2060 because it's mostly linked to the ITER timeline as well too. The fusion companies, which makes sense, it's like, of course they've got the most aggressive timelines. It's like, we're going to map the human genome faster as well too, right? So it's interesting about where we are. And I think, we're not all the way there, but my intuition tells me we're probably going to have a couple of cracks at it actually on that timeline. So this is where we have to be careful though. You say commercial fusion. What does that mean? Commercial fusion to me means that you actually have a known quantity about what it costs to build and what it costs to operate, and the reliability of putting energy on the grid. That's commercial fusion. It's like, so it turns out that that's not necessarily exactly the first fusion devices that put electricity on the grid, because there's a learning curve to get like better and better at it. But that's probably, I would suspect, the biggest hurdle is to get to the first one.
The work I've done the work I continue to do with autonomous vehicles and semi-autonomous vehicles. There's an interesting parallel there where a bunch of companies announced a deadline for themselves in 2020, 21, 22, and only a small subset of those companies have actually really pushed that forward. There's Google with Waymo, or Alphabet rather, and then there's Tesla with semi-autonomous driving in their autopilot full self-driving mode. And those are different approaches. So Tesla is achieving much, much higher scale, but the sort of the quality of the drive is semi-autonomous, right? I don't know if there's a metaphor, an analogy here.
Yep.
And then there's Waymo that's focusing on very specific cities, but achieving real full autonomy with actual passengers, but the scale is much smaller. So I wonder, just like you said, there'll be these kinds of similar kind of really hard pushes.
Absolutely. So actually, this is it's why I'm encouraged about fusion. So fusion's still hard. Let's let everyone be clear, because of the science underneath it of achieving the right conditions for the plasma, basically is a yardstick that you have to put up against all of them. What's encouraging that I see in this, and it's actually what happens when you sort of let loose the creativity of this, is maybe I'll go back to first principles. So fusion is also a fairly strange. So if you think about building a coal plant, like burning wood and coal and gas is actually not that much different from each other, because they're kind of about the same physical conditions, and you get the fuel and you light it. Fusion is remember I told you that there's this condition of the temperature, which is kind of universal. But if you take the density of the fuel between magnetic fusion and inertial fusion, they're different by about a factor of 10 billion.
Mm-hmm.
So the density of the fuel really matters. And actually, so does this means the energy confinement time is also different by a factor of 10 billion as well, too, because it's the product of those two. So one's really dense and short-lived, and the other one's really long-lived and actually under-dense as well, too. So what that means is that the way to get the underlying physical state is so different among these different approaches. What it lends itself to is, does this mean that eventual commercial products will actually fill different needs in the energy system? So it sort of goes to your comment about, I have to suspect this. It's like, because anything that is high tech and is and a really important thing in our economy tends to never find its way as only one manifestation. Like, look at transportation as well too. We have scooters, Vespas, overland trucks, cars, electric cars. Of course we have these because they meet different demands in it. So what's interesting, that I find fascinating now is that we have in fusion, it's going to look like that probably there's while the near term focuses on electricity production, there might even be different kinds of markets that actually make sense in some places, less in others. It comes to trade-offs, because we haven't really talked about the engineering yet, but the engineering really matters, like to the operation of the device. And so it could be I suspect what we'll end up with is several different configurations which have different features, which are trade-offs basically in the energy market.
What do you see as the major engineering or general hurdles that are in the way?
Yeah. So the first one is just the cost of building a single unit. So fusion has, and it's actually interesting you talked about the different models that you have. So fusion has one of its interesting limitations is that it's very hard. It almost at some point becomes physically impossible to actually make small power units. Like a kilowatt, 1,000 watts, which is like a personal home, is about 1,000 watts, or your personal use of energy of electricity is about like 1,000 watts. This is basically impossible for a single unit to do this. So you're not going to have a fusion power plant as your furnace or your electric heater in your home. And the reason for this comes from the fact that fusion relies on it being, it's not just that it's very hot, it's that the fusion power is the heating source to keep it hot. So if you go too small, it basically just cannot keep it hot. So it's interesting is that this is one of the hard parts. So this means that the individual units, and it varies from concept to concept, but the National Academy's report that came out last year sort of put the benchmark as being like probably the minimum size looks like around 50 million watts of electricity, which is like enough for like a small to, mid-sized city actually.
Mhm.
So that is so that's sort of like a scale challenge, and in fact, it's one of the reasons why in Commonwealth and in other private sector ones, like they try to push this down actually of trying to get to these smaller units, just because it reduces the cost of it. Then probably, obviously, I would say it's an obvious one, like achieving the fusion state itself and high gain is a hard one, but we already talked about.
What kind of hurdle, what kind of challenge
Well,
is that?
that's achieving the right temperature, density, and energy confinement time in the fuel itself, in the plasma itself. And so some of the configurations which are being chosen have quite a ways to go. In fact, I've seen those, but what their consideration is, oh yes, but by our particular configuration, the engineering simplicity confers like an economic advantage, even if we're behind in sort of in a science sense. Okay, which is fine. This is also what you get when you get an explosion in the private sector. You basically are distributing risks in different ways, right? Which makes sense. All of that good. But so what I would say is that the next hurdle to really overcome is about making net electricity. So like we need to see a unit or several units like using fusion in some way to put a meaningful amount of energy on the grid, because this starts giving us real answers as to like what this is going to look like.
The full end-to-end process.
The full end-to-end thing. So Commonwealth's goal is that I'll just comment to Commonwealth because I'll take some credit for this, is that the origins of Commonwealth were in fact in examining that. Like we could see this new technology coming forward, this new superconducting material, and the origins of our thought process were really around designing effectively the pilot plant or the commercial unit. It's called ARC, which is actually the step forward after SPARC, and that was the origins of it. So all the things that were other parts of the plan, like SPARC and the magnet, were actually all informed totally by building something that's going to put net electricity on the grid. And the timing of that, we still hope, is actually the early 2030s.
So SPARC is the design of the tokamak, and ARC is the actual full end-to-end thing.
It is like a thing that actually puts that energy on the grid. So SPARC is named, intentionally, that it's like it's on for a short period of time, and it doesn't have it has, it's the spark of the fusion, revolution or something like that, I guess we could call it. So those are sort of the programmatic challenges of doing that. And it's you talked about SpaceX. So what has evolved even in the last year or so was, in fact, in March of 2022, the White House announced that it was going to start a program that kind of looks like a SpaceX analogy, that namely, wow, we've got these things in the private sector. We should leverage the private sector and the advantages of what they obtain, but also with the things like this is going to be hard and it's going to take quite a bit of financing. So why don't we set up a program where we don't really get in the way of the private sector fusion companies, but we help them finance these difficult things, which is how SpaceX basically became successful through the COTS program. Fantastic, right? And that's evolving as well too. So like the fusion ecosystem is almost unrecognizable from where it was like 5 years ago around those things.
How important is it for the heads of the companies that are working on nuclear fusion to have a Twitter account and to be quite? You said you don't use Twitter.
I don't use Twitter
very much. I mean, there is some element to, and I don't think this should be discounted. Whatever you think about figures like Jeff Bezos with Blue Origin or Elon Musk with SpaceX, there is a science communication, to put it in nice terms, that's kind of required to really educate the public and get everybody excited and sell the sexiness of it. I mean, just even the videos of SpaceX, just being able to kind of get everybody excited about going out to space once again. I mean, there's all kinds of different ways of doing that, but I guess that's what companies do well, is to advertise themselves, to really sell themselves.
It is, yeah. Well, actually, like I feel like one of the reasons on this podcast, and so like I don't have an official role in the company, and one of the reasons for this was also that it's interesting because when you come from like you're running a company, it makes sense that they're promoting their own product and their own vision, which totally makes sense. But there's also a very important role for academics who have knowledge about what's going on, but are sufficiently distant from it that they're not fully only self-motivated just by their own, projects or so
Sure.
forth. And for me, this is, I mean, we see particularly the problems of the distrust in technology, and then honestly in the scientific community as well too. It will be one of the greatest tragedies, I would say, that if we go through all of this and almost pull off what looks like a miracle, like technologic and scientific wise, which is to make a fusion power plant, and then nobody wants to use it because they feel that they don't trust the people who are doing it or the technology. So we have to get so far out ahead of this. So I give lots of public lectures or things like this of accessing a larger range of people. We're not trying to hide anything. You can come and see, come do tours of our laboratory. In fact, I want to set those up virtually as well too. You might look at our Plasma Science and Fusion Center YouTube channel. So we are reaching out through those media.
Great.
And it's really important that we do those things. But it's also then realizing, setting up the realistic expectations of what we need to do. We're not there. We don't have commercial fusion devices yet. And you asked, what are the challenges? I'm not going to get into any deep technical, questions about what the challenges are, but the pathway, not just to make fusion work technically, but to make it economically competitive and viable so that it's actually used out in the private sector, is a non-trivial task. And it's because of the newness of it. We're simultaneously trying to evolve the technology and make it economically viable at the same time. Those are two difficult coupled tasks. So my own research and my own drive right now is that fantastic Commonwealth Fusion Systems is set up. We have a commercialization unit of that particular kind, which is going to drive forward a tokamak. In fact, I was just there's discussions, or there's dialogues going on around the world with other kinds of ones like stellarators, and so, which prefer different kinds of challenges and economic advantages. But I know what we have to have. What we have to have is a new generation of integrated scientists, technologists, and engineers that understand what needs to get done to get all the way to the goal line. Because we don't have them now.
So a multidisciplinary team.
Yeah, exactly.
What's required? I mean, you've spoken about. You said that fusion is, quote, the most multidisciplinary field you can imagine.
Yes. Yeah.
Why is that? What are the differences?
Yeah, well, because most of our discussion that we've had so far is really a physics discussion, really. So, which don't neglect physics, is at the origin of this. But already we touched on plasma physics and nuclear physics, which are basically two, somewhat overlap but independent disciplines. Then when it comes to the engineering, it's almost everything. So why is this? Well, let's build an electromagnet together. Okay. What is this going to take? It's going to take, it's basically electrical engineering, so you understand about how it goes together, what happens. Computational engineering to model this very complex integrated thing. Materials engineering, because you're pushing materials to their limit with respect to stress and so forth. It takes cryogenic engineering, which is sort of a subdiscipline, but cooling things to extremely low temperatures.
There's probably some kind of chemistry thing in there too.
Well, actually, yeah, which tends to show up in the materials, and that's just one of the subcomponents of it. Almost everything gets hit in this, right? So you're also in a very integrated environment, because in the end, all of these things, while you isolate them from each other in a physics sense, in an engineering sense, they all have to work seamlessly together. So it's one of those. In my own career, I've basically done atomic physics, spectroscopy, plasma physics, ion etching, so this includes material science, something called MHD, magnetohydrodynamics, and now all the way through, I'm not even sure how many different careers I've had. It's also, by the way, this is also a recruiting stage for young scientists thinking to come in. My comment to scientists, if you're bored in fusion, you're not paying attention, because there's always something interesting to go and do. So that's a really important part of what we're doing, which isn't new in fusion actually, and in fact is in the roots of what we've done at MIT. But holy cow, the proximity of possibility of commercial fusion is the new thing. So my catchphrase is like, you maybe wonder, like, why weren't we doing all these things? Like, why weren't we pushing towards economic fusion and new materials and new methods of heat extraction and so forth? Because everybody knew fusion was 40 years away. And now it's 4 years away.
There is a history, like you said, 40, 30, whatever, the kind of old joke. There's a history of fusion projects that, are characterized by cost overruns and delays.
Yeah.
How do you avoid this? How do you minimize the chance of this?
You have to build great teams, is one of them. It tends to be that the smaller there's sort of I'm not an expert in this, but I've seen this enough integrated.
Is there an equation?
Yeah. Well, I've seen this from enough teams. Like I've seen also the futility of lone geniuses trying to solve everything by themselves. No. But also organizations that have 10,000 people in them is just doesn't lend itself at all to innovation. So like one of our original sponsors and a good friend, Vinod Khosla. I don't know if you've ever talked to Vinod Khosla. He's a venture guy. He's got fantastic ideas about like the right sizes of teams and things that really innovate, right? And there is an optimum place in there, is that you get enough cross-discipline and ideas, but it doesn't become so overly bureaucratic that you can't execute on it. So one of the ways, and this was one of the challenges of fusion, is that everything was leading towards like I have to have like enormously large like teams just to execute because of the scale of the project. The fact that now through both technology and I would argue financing innovation, we're driving to the point where it's smaller, focused teams about doing those things. So that's one way to make it faster. The other way to make it faster is modularize the problem or parse the problem. So this is the other difficulty in fusion, is that you tend to look at this as like, oh, it's really just about making the plasma into this state, here that you get this energy gain. No. Because in the end, if you can parse out the different problems of making that and then make it as separate as possible from extracting the energy and then converting it into electricity, the more separate those are, the better they are, because you get parallel paths that basically mitigate risk. This is not new in fusion, by the way, and this is the way that we attack most complex technological, integrated technological challenges.
Have you, by any chance, seen some of the application of artificial intelligence, reinforcement learning? DeepMind has a nice paper, has a nice effort on basically using reinforcement learning for a learned control algorithm for controlling nuclear fusion.
Yeah.
Do you find those kinds of, I guess you throw them under the umbrella of computational modeling. Do you find those interesting, promising directions?
They're all interesting. So when people, I'll pull back. Maybe a natural question is like, why is it different in fusion? Like there's a long history to fusion, right? It was going on for, like I told you, like stories from the late 1960s. Like what's different now, right? So I think from the technology point of view, there's two massive things which are different. So one of them, I'll be parochial. It's the advent of this new superconducting materials, because the most mature ways that we understand about how we're going to get to fusion power plants are magnetic fusion. And by the fact that you've got access to something which like changes the economic equation by an order magnitude is just a totally, and that wasn't that long ago. It was only September of 2021 that we actually demonstrated the technology. That changes the prospects there. And the other one is computing. And it's across the whole spectrum. It's not just in control of the fusion device. It's actually we actually use machine learning and things like this in the design of the magnet itself. It's an incredibly complex design space. So you use those tools. The simulation of the plasma itself is actually, we're at a totally different place than we were because of those things. So those are the two big drivers that I see actually that make it different. And it's interesting, both those things self-enforce about what you asked about before, like how do you avoid delays and things? Well, it's by having smaller teams that can actually execute on those. But now you can do this because the new magnets make the devices all smaller, and the computing means your human effectiveness about exploring the optimization space is way better. It's like they're all interlinked to each other.
Plus the modularization, like you said, and it's everything just kind of works together to make smaller teams more effective, move faster.
And it's actually, and it's through that learned experience. I mean, of the things that I'm the most proud of about what came out. In fact, the origins of thinking about how we would use the high temperature superconducting magnets came out of my design class at MIT. And in the design class, like one of the features that I kept, I mean, it was interesting. I really learned along with the students about this, but like this insistence on the features, like we can't have so many coupled, integrated, hard technology developments. Like we have to separate these somehow. So we worked and worked and worked at this. And in fact, that's what really, in my opinion, the greatest advantage of the ARC design and and built into the Commonwealth fusion system idea is like to parse out the problems. Like how can we attack these in parallel? Yeah, and so it really comes to we talked about philosophy. It's like a design philosophy. Like how do you attack these kinds of problems? And you do it like that.
And also, like you mentioned offline, that there's a power to, as part of a class, to design a nuclear fusion power plant.
Well,
and then make it a
is
reality.
And it's hard to imagine a more powerful force than like 15 MIT PhD students like working together towards solving a problem. And what I always, in fact, we recently just taught the most recent. I say I teach it. I mean, I guide it actually. Yeah. The most recent version of this, where they actually designed, based on this National Academies report, they actually designed like a pilot plant that has basis and similarities to what we had done before. But, I kept wanting to like push the envelope and where they are. It's like the creativity and the energy that they bring to these things is kind of like, it keeps me going. Like I'm not going to retire anytime soon when I keep seeing that kind of dedication, and it's wonderful around on that. It almost, not to overuse or to paraphrase something, right? Which is that, the famous quote by Margaret Mead, never doubt that a small group of dedicated, persons will change the world. Indeed, it's the only thing that ever has.
I mean, that's just such a powerful and inspiring thing for an individual. Find the right team, be part of that, and then you yourself, your passion, your efforts could actually make a big change.
Yeah.
A big impact. I got to ask you, so it's a whole nother different conversation I'm sure to have, but nuclear power as it currently stands, so using fission is extremely safe despite public perception.
It is the safest, actually.
So that's a whole nother conversation, but almost like a human bureaucratic physics engineering question of what lessons do you draw from the catastrophic events where the power plants did fail. So Chernobyl and 3 Mile Island. Chernobyl, what lessons do you draw?
Actually, 3 Mile Island wasn't really a disaster because nothing escaped from the thing. But Chernobyl and Fukushima had obvious consequences in the populations and that live nearby.
What lesson do you draw from those that you can carry forward to fusion? Now, I know you can say that you're not going to have the same kind of issues, but it's possible that the same folks also said they're not going to have those same kind of issues.
Yeah.
We humans, the human factor, we haven't talked about that one quite as much, but it's still there.
Yeah. So to be clear, so fusion has the intrinsic safety with respect to it can't run away. Those are physics bases. Technology and engineering basis of running again, anything that makes large amounts of power and heats things up has got intrinsic safety in it. And by the fact that we actually produce very energetic particles. This doesn't mean that there's no radiation involved in ionizing radiation, to be more accurate, in fusion. It's just that it's in a very different order of magnitude, basically. So what are the lessons in fusion? So one of them is make sure that you're looking at aspects of the holistic environmental and societal footprint that the technology will have. As technologists, we tend not to focus on these, and particularly in early stages of development. Like we just want something that works, right? But if we come with just something that works but doesn't actually satisfy the societal demands for safety and for we will have materials that we have to dispose of out of fusion. But there's technological questions about what that looks like. So will this look like something that you have to, put in the ground for 100 years or 5 years? And the consequences of those are both economic and societal acceptance and so forth. But don't bury those. Bring these up front, talk to people about them, and make people realize that you're actually The way I would look at it is that you're making fusion more economically attractive by making it more societally acceptable as well too. And then realize is that, I think there's a few interesting, boundaries basically in this. So one of them, speaking of boundaries, is that successful fusion devices, I'm pretty sure will require that you don't have to have an evacuation plan for anybody who lives at the site boundary.
Mm-hmm.
So this has implications for what we build from a fusion engineering point of view, but it has major implications for where you can site fusion devices, right? So in many ways, it becomes more like, well, we have fences around, industrial heat sources and things like this for a reason, right? For personal safety. It looks more like that, right? It's not quite as simple as that, but that's what it should look like. And in fact, we have research projects going on right now at MIT that are like trying to push the technologies to make it more look like that. I think that those are key. And then in the end, as I said, so Chernobyl is physically impossible, actually, in a fusion system.
From a physics perspective.
From a physics perspective, you can't run away like it did at Chernobyl, which was basically human error that, of letting the reactors run out of control, essentially.
Human error can still happen with fusion-based reactors.
So, but in that one, if human error occurs, then it just stops, and this is done. And all of those things, this is the requirement of us as technologists and developers of this technology to not ignore that dimension, in fact, of the design. And that's why, me personally, I'm actually pouring myself more and more into that area, because this is going to be, I actually really think it is an aspect of the economic viability of fusion, because it clearly differentiates ourselves and also sets us up to be about what we want fusion to be. Is that, again, on paper, fusion can supply all of our energy, all of it. So this means I want it to be like really environmentally benign, but this takes engineering ingenuity basically to do that. Yeah.
Let me ask you some wild out there questions.
Sure.
So
we've been talking too much,
It's a simple, practical things in everyday life. No, only revolutionizing the entire energy infrastructure of human civilization. Yes, but so cold fusion.
Yeah.
This idea, this dream, this interesting physical goals seem to be impossible, but perhaps it's possible. Do you think it is possible? Do you think down the line, somewhere in the far distance, it's possible to achieve fusion at low temperature?
It's very, very, very unlikely. And this comes from, so this would require a pretty fundamental shift in our understanding of physics, as we know it now. And we know a heck of a lot about how nuclear reactions occur. But by the way, what's interesting is that they actually have a different name for it. They call it leaner, low energy nuclear reactions. But we do have low energy nuclear reactions. We know these. It's because these come from particularly the weak interaction, the weak force, nuclear force. And so it's at this point, as a scientist, you always keep yourself open but you also demand proof, right? And that's the thing.
It almost requires a breakthrough on the theoretical physics side. So some deeper understanding about quantum mechanics, something, so the quantum tunneling, some weird.
Yeah, and people have looked at that, but even something like quantum tunneling has a limit as to what it can actually do. So there are people who are genuine, that really want to see it make it, but it sort of goes to the extraordinary. I mean, we know fusion happens at these high energies. We know this extremely accurately, and I can show you a plot that shows that as you go to lower and lower energy, it basically becomes immeasurable. So if you're going down this other pathway, it means there's really a very different physical mechanism involved. All I would say is that I actually poke in my head once in a while to see what's going on in that area. And as scientists, we should always try to make ourselves open. But in this one, it's but show me something that I can measure and that it's repeatable, and then it's going to take more extraordinary effort. And to date, this has not met that threshold, in my opinion. Yeah.
So I'm even more so than just mentioning, or in that question, thinking about people that are claiming to have achieved cold fusion. Yeah. I'm more thinking even about people who are studying black holes, and they're basically trying to understand the function of, theoretical physicists.
Yeah.
They're doing the long haul,
Look,
trying to
yeah.
investigate, like, okay, what is happening at the singularity? What is this kind of holographic projections on a plate? These weird freaking things that are out there in the universe, and like somehow accidentally they start to figure out something weird.
Yeah.
And then all of a sudden,
there's weirdness all over the place already. Yeah.
Somehow that weirdness will,
Yeah.
I think on a time scale probably of 100 years or so, that weirdness will open.
Yeah.
So it just seems like nuclear fusion and black holes and all of this are they're next door neighbors a little bit too much for like you'll find something interesting.
Well, let me tell you a story about this.
Yes.
Okay. It's a real story. Okay. So there were really, really clever scientists in the end of the late 1800s in the world. You talk about like James Clerk Maxwell, and you talk about Lord Kelvin, and you talk about Lorentz, actually, who named after these other ones, and on and on and on, and like Faraday, and they discovered electromagnetism. Holy cow! And it's like they figure out all these things, and yet there were these weird things going on that you couldn't quite figure out. It's like, what the heck is going on with this, right? But we teach this all the time in physics classes, right? So what was going on? Well, there's just a few kind of things unchecked, but basically we're at the end of discovery because we figured out how everything works. Because we've got basically Newtonian mechanics, and we've got Maxwell's equations, which describe basically how matter gets pushed around and how electromagnetism works. Holy cow, what a feat. But there are these few nagging things. Like, for instance, there's certain kinds of rocks that for some reason, like if you put a photographic plate around it, it like gets burned or it gets an image on it. Like, well, where's the electromagnetism in that? There's no electromagnetic properties of this rock. Oh yeah, and the other thing too is that if I take this wonderful classical derivation of how of something that is hot, about how it releases radiation, everything looks fantastic, perfect match. Oh, until I get to high frequencies of the light. And then it basically just, the whole thing falls apart. In fact, it gives a physical explanation, which is total nonsense. It tells you that every object should basically be producing an infinite amount of heat. And by the way, here's the sun, and we can look at the sun and we can figure out it's made out of hydrogen. And Lord Kelvin actually made a very famous, calculation, who was basically one of the founders of thermodynamics. So you look at the hydrogen. Hydrogen has a certain energy content. The latent heat, basically, of hydrogen. We know the mass of the sun because we knew the size of it. And he conclusively proved that basically the sun could only make net energy for about 2,000 or 3,000 years. So therefore, all this nonsense about like deep is like, because clearly the sun can only last for 2,000 or 3,000 years. If you think about and this is basically the chemical energy content of hydrogen, and what comes along in 1 decade. Basically, one guy sitting in a postal office, in Switzerland, figures out that all of these, Einstein, of course, which was like figured out all this, took these seemingly unconnected things, and it's like, boom, there it is. This is what, it wasn't just him, but it was like, there's quantum physics. Like, this explains this other disaster. And then this other guy, my hero, Ernest Rutherford, experimentalist, did the most extraordinary experiment, which was that, okay, they had these funny rocks. They emitted these particles. In fact, they called them alpha particles. Alpha, just A in the alphabet, right? Because it was the first thing that they discovered. And what were they doing? So they were taking these alpha particles, and by the way, I do this to all my students because it's a demonstration of what you should be as a good scientist. So he took these alpha things, and he was a classically trained physicist, knew everything about momentum scattering and so forth like that. And he took this, and these alpha, which clearly were some kind of energy, but they couldn't quite figure out what it was. So he said, let's try to figure that. We'll actually use this to try to probe the nature of matter. So he took these alpha particles and a very, very thin gold foil. And so what you wanted to see was that as they were going through, the way that they would scatter based on classical, in fact, a Coulomb collision, based on classical mechanics, this will reveal something about what the nature of the charge distribution is in matter, because they didn't know, like, where the hell is this stuff coming from? Even though they'd solved electromagnetism, they didn't know, like, what made up charges. Okay, very interesting. On through it goes, And so what did you set up? So it turns out in these experiments, what you did was, because if these so-called alphas, which actually now we know is something else, as they go through, they would deflect. How much they deflect tells you how strong an electric field they saw. So you put detectors, because if you put like a piece of glass in front of this, what will happen is that when the alpha particle hits, it literally gives a little boop, a little of light like this. It scintillates, a little blue flash. So he would train his students or postdocs or whatever the heck they were at the time. You have to train yourself, because you have to put yourself in the dark for like hours to get your eyes adjusted. And then they would start the experiment, and they would sit there and literally count the things. And they could see this pattern developing, which was revealing about what was going on. But there was also another part to the experiment, which was that it's like, here's the alphas, here's the source. They're going this way. They could tell they were going in one direction only, basically. They're going in this direction. And you put all these over here because you want to see how they deflect and bend through it. But you put a control in the experiment, but you basically put glass plates back here, because obviously everything should just deflect, but nothing should bounce back. So it's a control in the experiment. Mm-hmm. But what did they see? They saw things bouncing back. Like, what the hell? Like, that fit no model of any idea, right? But Rutherford like refused to like ignore what was a clear, like they validated it, and he sat down, and based on classical physics, he made the most extraordinary discovery, which was the nucleus, which is a very, very strange discovery. What I mean by that, because what he could figure out from this is that in order for these particles to bounce back and hit this plate, they were hitting something that must be heavier than them, and that basically something like 99.999% of the mass of the matter that was in this gold foil was in something that contained about 1/1,000,000th of the volume of it. Mm-hmm. And that's called the nucleus. And you talk about, so how revealing is this? It's like, this totally changes your idea of the universe, because a nucleus is a very non-intuitive thing. It's like, why is all the mass in something that is like zero? Like, it basically is the realization that matter is empty. Mm-hmm. It's all empty space.
Yeah, and that changes everything.
And it changes everything. Until you had that, like you had steam engines, by the way, you had telegraph wires, you had all those things. Yeah. But that realization, like, opened up, those two realizations opened up everything. Like lasers, all these, think about the modern world of what we use. And that set it up. So all I would point out is that there's a story already that sometimes there's these nagging things at the edge of science that, we pat ourselves on the back and we think we got everything under control. And of course, that, by the way, that was the origin of also think about this, that was 1908. It took like another 20 some years before people put that together with, that's the process that's powering stars. Mm-hmm. It was the rearrangement of those nuclei, not atoms. That's why Kelvin wasn't wrong. He was working with the wrong assumptions, right? So fast forward to today, like, what would this mean, right? Well, there's a couple of things like this that sit out there in physics, and I'll point out one of them, which is very interesting. We don't know what the hell makes up 90% of the mass in the universe. Mm-hmm. So the search for dark matter, right? Mm-hmm. What is it? We still haven't discovered it. Yeah. 90% of the mass of the universe is undetectable. Like, what?
And then, and dark energy, and again, black holes are the window into this.
Well, then black hole. I mean, in some sense, black holes are way better understood than those things as well, too. So all it tells us is that we shouldn't have hubris about the ideas that we understand everything. And when we, who knows what the next major intellectual insight will be about how the universe, functions.
And actually, I think Rutherford is the one who's attributed at least that quote, that physics is the only real science, everything else is stamp collecting, right? So there's...
I'm sorry, he's my hero, but I'll slightly disagree with that, yes.
Well, no offense to stamp collecting, it's very important too. But you have to have humility about the kind of disciplines that make progress at every stage in science.
Yeah, exactly.
That physics did make a huge amount of progress in the 20th century, but it's possible that other disciplines start to step in.
Yeah, but Rutherford couldn't imagine like mapping the human genome because we didn't even know about DNA.
Yeah. Or computers, really.
Or computers.
He really probably didn't think deeply about computation.
It's like, here's a wild one. What if like the next great revelation to humanity about the universe is not done by the human mind.
That seems increasingly
Likely.
more
Yeah,
likely.
yes, yeah.
And then you start to ask deep questions about what is the purpose of science. For example, if AI system will design a nuclear fusion reactor better than humans do, but we don't quite understand how it works. And the AI can't, we know that it works. We can test it very thoroughly, but we don't know exactly what the control mechanisms is, maybe what the chemistry, the physics is. AI can't quite explain it. They just can't. It's
impenetrable to our consciousness, basically, of trying to hold it all together.
And then, okay, so now we're living in that world where many of the biggest discoveries are made by AI systems.
Yeah.
As if we weren't going big.
I say, it's, again, I'll point out, like, when my godmother was born, like, none of this was in front of us, right? It's like, we live in an amazing time. It's like, right, like my grandfather, plowed, fields with a horse. I get to work on designing fusion reactors. Yeah, pretty amazing time.
But still, there's humans, so we'll see. We'll see if that's around 100 years. Maybe it'll be cyborgs and robots.
I think we're pretty resilient, actually.
Yeah, I know. That's one lesson from life, is it finds a way.
Yeah.
Let me ask even a bigger question, as if those weren't big enough. Let's look out maybe a few hundred years, maybe a few thousand years out. There's something called the Kardashev scale. It's a method of measuring civilization's level of technological advancement based on the amount of energy it's able to use. So type 1 civilization, and this might be, given all your work, is no longer a scale that quite makes sense, but it very much focuses on the source of fusion, natural source of fusion, which is for us the sun. And type 1 civilizations are able to leverage, sort of collect all the energy that hits Earth. And then type 2 civilizations are the ones that are able to leverage the entirety of the energy that comes from the sun by maybe building something
like a Dyson sphere. Yeah.
So when will we reach type 1 status? Is get to the level which we're, I think, maybe a few orders of magnitude away from currently. And in general, do you think about this kind of stuff? Is where energy is so fundamental to of life on Earth, but also the expansion of life into the universe.
Oh yeah. So one of the fun, on a weekend when I sat down and figured out what would it mean for interstellar travel, like to have a DT fusion. In fact, I talked about my design class. One of my design classes was how you use essentially a special configuration of a fusion device for not only traveling to, but colonizing Mars. Mm-hmm. So, because you talk about energy use being at the heart of civilizations, like, so what if you want to go to Mars not to just visit it, but actually like leave people there and make something happen? Mm-hmm. It needs massive amounts of energy. So what would that look like? And it actually transforms how you're thinking about doing that as well too. Oh yeah, so we do all those kinds of fun. And actually it was a fairly quasi-realistic actually.
So do you think it'll be nuclear fusion that powers the civilization on Mars?
Well, what we considered was something, so it turns out that there's thorium, which is a heavy element. So it's a so-called fertile element that we know. We still know fairly little about the geology of Mars in a deep sense. And we know that there's a lot of this on the surface of Mars. So one of the things we considered was what would happen, that it's basically a combination of a fusion device that actually makes fuel from the thorium. Oh. But the underlying energy one was fission itself as well too. So this is one of the examples of trying to be clever right around those things. Or what is it? This also means is like interstellar travel. It's like, oh yeah, that looks almost like impossible basically from an energy balance point of view. It's just because like the energy required that you have to transport to get there. Almost the only things that would work are DT fusion and basically annihilation. It's like Star Trek, right?
Your sense is that interstellar travel will require fusion power.
Oh, it's almost even impossible with fusion power, actually. It's so hard. It's so hard because you have to carry the fuel with you, and the rocket equation tells you about how much fuel you'll use to take. So what you end up with is like, how long does it take to go to these places? And it's like staggering, periods of time.
So I tend to believe that there's alien civilizations dispersed all throughout
Yeah, but we
the
might be
universe.
totally isolated from them.
So you think there's none in this galaxy? So like, and I guess, and the question I also have is, do you think they have nuclear fusion? It's like, is the physics all the same?
Yeah. Oh, the physics is all the same. Yeah. Right. So this is the Fermi paradox. Like, where the hell is everybody in the universe? Right? Well, there's the scariest one of those is that I would point out that there's been, there's, order of many tens of millions of species on the planet Earth, and only one ever got to the point of sophisticated tool use that we could actually start essentially leveraging the power of what's in nature to our own will. Does this mean that basically this means there is almost certainly life or DNA equivalents or whatever it would be somewhere. I mean, just because you just need a soup and you need energy and you get organics and whatever the equivalent of amino acids are. But most of the life on Earth has been those are still amazing, but it's still like it's not very interesting. Are we actually the accident of history? This is a very interesting one.
Super rare accident.
Super rare. And then, of course, the other part is that also just the other scary part of it, which if you look at the Fermi paradox is, good, we got to this point. How long has it been in humans? So humans, Homo sapien has been around for whatever, 100,000 years, 200,000 years, something like that. Our ability in that timeline to actually make an imprint on the universe, by emitting radio waves or by modifying, nature in a significant way, has only been for about 100 of those 100,000 years. And it's a good question. So is it by definition that by the fact that when you are able to reach that level of being able to manipulate nature and, for example, discover like fission or other or burning fossil fuels and all this, is that what it says? Oh, you're doomed, because by definition, any species that gets to that point that can modify their environment like that, they'll actually push themselves past. That's one of the most depressing scenarios that I can imagine.
Yeah. So
so basically, we will never line up in time, because you get this little teeny window in time of where civilization might occur, and you can never see it because you never. These sort of like scatter like fireflies around the galaxy, and you never
builds up, and then explodes, destroys itself because of the exponential.
And when we say destroy ourselves, all would have to do is that we basically go, if humans are all left and we're still living on the planet, but all we have to do is go to the technology of 1800, and we're invisible in the universe again.
Yeah.
So it was when I listened to I thought I wanted to talk about this as well too, because it comes from a science point of view actually of what it means, but also to me it's like another compelling driver of telling us it's like why we should try really hard not to screw this up. Like we're in this unique place of our ability to discover and to make it, and I just don't want to give up about thinking that we can get through.
Yeah, I tend to see that there is some kind of game theoretic force, like with mutually assured destruction, that ultimately in each human being there's a desire to survive and a willingness to cooperate, to have compassion for each other in order to survive. And I think that, I mean, maybe not in humans, but I can imagine a nearly infinite number of species in which that overpowers any technological advancement that can destroy or rewind the species. So I think if humans fail, I hope they don't. I see a lot of evidence for them not, but it seems like somebody will survive. And there you start to ask questions about why we haven't met yet. Maybe it's just space is large.
Oh, space is, I think in logarithms, and I can't even fathom, space. This is extraordinary, right?
Yeah.
It's extraordinarily large. Yeah.
I mean, there's so many places on Earth. I just recently visited Paris for the first time.
Yeah.
And there's so many other places I haven't visited.
There's so many other places. Well, I like to, it's interesting that we have this fascination with alien life. We have what is essentially alien life on Earth already. Like you think about the organisms that develop around deep sea, like thermal vents. One of my favorite books of all time from Stephen Jay Gould. If you've never read that book, it kind of blows your mind. It's about the Cambrian explosion of life. And it's like, oh, you look at these things and it's like, the chance of us existing as a species, like the genetic diversity was larger back then.
Mhm.
This is about 500 million years ago or something like that. It is a mind-altering trip of thinking about our place in the universe, I have to say.
Plus, the mind itself
Yeah.
is a kind of alien with almost a mystery to ourselves. We still don't understand it. The very mechanism that helps us explore the world is still a mystery.
Yeah.
So that, like, understanding that will also unlock, quite possibly unlock our ability to understand the world, and maybe build machines that help us understand the world, build tools that help us
I mean, it already has. I mean, our ability to understand the world is ridiculous, almost, actually.
and post about it on TikTok.
It's almost unbelievable, like where we've gotten all this to. Yeah.
So, what advice would you give to young folks or folks of all ages who are lost in this world, looking for a way, looking for a career they can be proud of, or looking to have a life they can be proud of?
Yeah. Oh, the first thing I would say is don't give up. I get to see multiple sides of this, and there seems to be a level of despair in a young generation. It's like it's almost like the Monty Python skit, like, I'm not dead yet, right? I mean,
Yeah.
like we're not there. We're in a place that don't say the world's going to end in 300 days or something. It's not, okay. And when we mean by this is that we have a robust society that's figured out how to do like amazing things, and we're going to keep doing amazing things. But that shouldn't be complacency about what our future is, and the future for their children as well too. And in the end, I mean, it's a staggering legacy to think of what we've built up, primarily by basically using carbon fuels. Like, people almost tend to think of this as an evil thing that we've done.
Mm-hmm.
I think it's an amazing thing that we've done. But we owe it to ourselves and to this thing that we've built. I mean, talking about the end of the world is this nonsense. What it is it's the end of this kind of lifestyle and civilization at this scale, and the ability to execute on these kinds of things that we are talking about today. Like, we are extraordinarily privileged. We are in a place where it's almost unfathomable compared to most of the misery that humans have lived in for our history. So don't give up about this, okay? But also roll up your sleeves and let's get going at solving and getting real solutions to the problems that are in front of us, which are significant. I would argue most of them are linked to what we use in energy, but it's not just that. It's around all the aspects of, like, what does it mean? Like, what does it mean to have a distributed energy source that lifts billions of people out of poverty, particularly outside of, like, the Western nations, right? That seems to me a pretty compelling, moral goal for all of us, but particularly for this upcoming, generation. And then the other part is that we've got possible solutions in front of us. Apply your talents in a way that you're passionate about and is going to make a difference.
And that's only possible with optimism, hope, and hard work.
Yeah.
What easy question, certainly easier than nuclear fusion. What's the meaning of life? Why are we here?
42.
Is it 42?
No.
We already discussed about the beauty of physics, that there's almost a desire to ask a why question about why the parameters have these values.
Yeah. It's very tempting. Yeah. It's an interesting hole to go down as a scientist, because we're a part of what people have a hard time, people who aren't scientists have a hard time understanding what scientists do to themselves. And a great scientist does a very non-intuitive or non-human thing. What we do is we train ourselves to doubt ourselves like hell. Like, that's a great scientist. We doubt everything we see. We doubt everything that we think, because we basically try to turn off the belief valve, right? That humans just naturally have. So when it comes to these things, like, I can make my own comments to this. It's like, personally, you see these things about the ratios of life, and I made a comment where I said, well, some part of my brain that just goes, yeah, because we're the only interesting, multiverse, because by definition it has to look like this,
Yeah.
But I have to say, there's other times I can say in the history of what has happened over the last 10 years, there have been some pretty weird coincidences, that like you look at it and just go, was that really a coincidence? Is something like pushing us towards these things?
Yeah.
And it's a human instinct, because, since the beginnings of humanity, we've always assigned, you know, human motivation and needs to these somewhat, empirical observations.
And in some sense, the stories, before we understand the real explanations, the stories, the myths, serve as a good approximation
Yeah.
for the thing that we're yet to understand.
Absolutely.
And in that sense, you said the antithesis to sort of scientific doubt is having a faith in these stories. They're almost silly when looked at from a scientific perspective, but just even the feelings of, it seems that love is a fundamental fabric of human condition.
Yeah.
And what the hell is that?
Well, actually,
why
I
are we
mean,
so connected to each
again,
other?
as a physicist, I go, it's, this is a repeatable thing
Yeah.
that's due to a set of synapses that
Yeah.
fire in a particular pattern and all this.
Yes.
That's kind of like, okay, man, what a drag that is, right? To think of it this way.
And you can have an evolutionary biology explanation, but there's still a magic to it.
I mean, I see scientists, some of my colleagues, do this as well too. Like, what is spirituality compared to science and so forth? My own feeling in this is that, as a scientist, because I've had the pleasure of being able to like both understand what my predecessors did, but I also had the privilege of being able to discover things, right, as a scientist. And I see that, and in just the range of our conversations, like that is in a weird way, it's the awe that comes from looking at that. That is, if you're not in awe of the universe and nature, you haven't been paying attention. I mean, my own personal feeling is that I feel, if I go snorkeling on a coral reef, I feel more awe than I could ever feel like in a church.
You kind of notice some kind of magic there.
There's something about the way the whole darn thing holds together that just sort of escapes your imagination. And that's, to me, this thing of, and then we have different words, we call them holistic or spiritual, the way that it all hangs together. In fact, one of the interesting, you asked about like what I think about, one of the craziest things that I think that how does it hold together is like our society.
Mm-hmm.
Like, how does, like, what?
Yeah.
Like, how are, because there's no way, like, you just think of the United States, there's 330 million people kind of working like this engine about going towards making all these things happen. But there's like no one in charge of this, really.
Not
right?
really, yeah.
How the heck does this happen? Yeah. It's kind of like, it's, so these things, these are the kinds of things mathematically and organization wise that I think of, just because they're awe-inspiring. Right?
And there's different ideas that we come up together and we share them, and then there's teams of people that share different ideas, and those ideas compete. Like the ideas themselves are these kinds of different organisms, and ultimately somehow we build bridges and nuclear reactors
and do those things. Well, I have to give a shout out to my daughter, by the way, who's interested. Yeah. She's an applied math major, and she's amazing at math. And over the break, she was showing me she's doing research, and it's basically about how ideas and ethos are transmitted within a society.
Nice.
So she's building an applied math model that is explaining, like, she was showing me in this simulation. She goes, "Oh, look at this," and I said, "Oh, that's like how political parties like evolve, right?"
Yeah.
And even though it was a rather, quote unquote simple mathematical model, it wasn't really. And it's like, oh, wow.
Well, maybe she has a chance to derive mathematically the answer to what's the meaning of life.
There we go.
And maybe it is indeed 42. Well, Dennis, thank you so much for just creating tools, creating systems, exploring this idea that's one of the most amazing, magical ideas in all of human endeavor, which is nuclear fusion. Yeah. I mean, that's so interesting.
It's almost like one of my lifelong goals is like to make it, it's like, it's not magic. It's like, it's boring as all heck. And this means we're using it everywhere, right?
Yeah.
Yeah.
And the magic is then built on top of it.
Yeah.
Well, thank you for everything you do. Thank you for talking to me. It's a huge honor. This was a fascinating and amazing conversation.
Thank you.
Thanks for listening to this conversation with Dennis Whyte. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Albert Einstein. There are two ways to live your life. One is as though nothing is a miracle. The other is though everything's a miracle. Thank you for listening. I hope to see you next time.